Okay, so it's
but
my assistant. Once again, you already know my name, Vadim. And the thing I'm gonna tell you about is actually not Raku syntax. Even though this class is for beginners, I'm not gonna tell you things like how to say hello world or how to write my $var a SIG42. No way. No things like this. I'm gonna try to tell you about the basic fundamental blocks of Raku and its implementation, Rakudo. At some points, I would be also referring to Perl, maybe, it depends. I'll try to tell things in a way that you wouldn't actually need to know Raku in deep. And actually, if you know just Perl, that's going to be fine too. Because basically, the syntax I'm going to use for examples is very basic syntax, pretty much understandable, and should be no problem to see the idea behind the code. Also, the presentation, which is I'm sharing currently, it's also more like a plan for myself, just not to forget the order to tell things. There will be some illustrations, but most of the information will be shared via code examples and verbally. And I'll be trying to follow the chat as well. So if you have any questions, you can ask them on the chat. And if you address them directly on my name in the chat, it's going to be easier for me to spot them, just because Zoom done it this way. But also I might spot some questions kept in the common chat. And the thing I'm going to start with, all the code examples, I keep them in a repository. So right now in the chat window, I provided you with URL for this repository, so you can check it out and you can follow me because I know that sometimes screen sharing doesn't provide very well quality. And even though I will try to use as big font as possible on the screen, still there might be some glitches and so on. So as soon as you know which file name I'm showing to you, you can watch it locally, see it locally, and check out against the source. Also, the repository contains some information in its README file, so I also recommend you to look at it. Good. And actually, it's not the last URL I'm going to be sharing on the chat window as well, so just follow it. First of all, the question which we must clearly understand, and the question is, what is Raku? I mean, what defines the language? It's pretty much confusing question for most developers. I don't know why. Maybe they expect to see some kind of specification like C++ has, which was total surprise to me when I found out that the specification of C++ is actually paywalled. You have to pay for it. Oops, I didn't know. Okay, good. They have books. Other languages like Rust, they have a book and a manual of some kind, which is official and which is considered, as far as I understand, to be its specification. Raku is totally different. absolutely different. I don't know any other language which does it the way Raku does it. In Raku, we have a set of tests which define the language. If you create a compiler for Raku, and this compiler can't pass this test suite, it means your compiler implements Raku language in full. So if you didn't know about it yet, then you can have a look at this URL, and that's where the test suite is kept. We call it roast. And while it might be not so convenient for a human being to read this kind of specification, reading tests is not the best way of learning something. Still, it's fantastically great for developing clean and stable language. It's the best, most definitely. So without roast, I have no idea. Many bugs would just slip away, uncode, and so on. So if you want to learn Raku, of course, you go find some book, you go find some manual, you go find somebody's help. But if you're gonna develop Raku, if you're gonna participate in Raku development, roast is definitely the thing you have to know about and you have to use extensively, and you will actually. For those who are interested in early stages of Raku development, just out of curiosity, it's pretty okay. Java, good. Java has something similar. Well, I'm not a big expert in other languages anyway. I mean, I try to follow, I try to read them, but still. So if you want to see how Raku was developed originally, then you can read those historical design documents on the URL I just provided. And they're actually called synopses. But let's move on. Another thing we must understand about Raku, also other languages has different versions. And Raku certainly has versions too. The first released Raku version was still named Perl 6, and it was 6C version. Currently, we have released 6D version, and 6E is currently in development. So when we technically use 6E, we append .preview to it at the moment because it's not released, it's in preview stage. Also, when we talk about language version, Raku language version, we sometimes use revision term separately. Revision is the letter following the 6. So revision C, revision D, revision E, just where we need some kind of short representation. So if I say language version of or language revision, it's basically the same thing, no difference. Now we switch to implementation. At the moment, the implementation we work on is named Rakudo. It's the primary one. And basically, I would say at the moment, it's the only one. There was some historical, but okay. Oops, sorry, it should have appeared. Okay. If you don't have Rakudo installed yet, I don't know, maybe somebody is total newbie, then you can find information about compiling Rakudo in the README file of my Raku Inside Out repository. That's the workflow I use myself because I work on Rakudo development pretty much lately. So I found this the most convenient way. I use it together with Raku Brew, which lets me to switch between different Rakudo versions easily. So when I do development, I found that something is wrong, and I know it wasn't wrong before. I can easily switch to another version of Rakudo and see what's going on. So I hope the treatment is sufficient, and we can skip this step and talk about more essential things. Oh, yes, I forgot to say one other thing pretty much important, as I see it. This class, I tried to base it on questions I was seeing from developers on Stack Overflow, on GitHub issues, and other locations. So subjects in this class try to cover those questions. And one of the biggest mistake people often do, beginners often do, they mess up Rakudo version and Raku version. I hope you currently see my terminal window. Yes, okay. So if you ask for a Rakudo version, you basically see, okay, let me switch to a non-build version. Okay, this one is cleaner. So you see 3 lines. You see actually Rakudo version, and the Rakudo version consists of year and months of the release build. And this is compiler version. But the second line, you see the Raku version. And this is the language version the current Rakudo implements by default. This is the language version you get when you do something like this. Say, sorry, I don't often use it. Compiler version. Okay, this is a get compiler version. Yeah. So as you can see, this is what you get by default. This is what your code, language version your code is supposed to comply to when you use a versionless script or code snippet or whatever else. So make clear distinction. We have a compiler and it has its own version. And this version basically changes every month with each new release. And Raku version is something different. It's, well, basically Raku version, it's what is spec'd in the roast. Okay, Raku brew I already mentioned about, and it's also in the README file in the repository. Sorry. And if you want, if you don't want to build Rakudo and you want just use it, of course, you can always go to rakudo.org website and download it from there. We currently have versions for Windows, Linux, macOS, probably FreeBSD, OpenBSD. I don't remember. There should be there. What about other implementations? As I told you, basically Rakudo is for the moment the only one. But historically, there was other implementations of, by then, Perl 6 language. There was Bugs, there was, don't even know how to pronounce it, Nieza, and a few others. If you're interested, you can see this URL in the chat and you can get a bit of history of Raku Perl 6 languages. But we focus on Rakudo implementation. another question. Oops, excuse me. Another question confusing newbies is, after all, is Raku interpreter or Rakudo actually, or a compiler? Well, I already said that it's compiler, but why is it so? You see, when I used this line, it actually acts as interpreter. And also I can, okay, let's do something, whatever. Or you can say it like this, and also you get output of your script instantly, right away, which is more inherent to interpreters actually. And people expect it to be an interpreter. In fact, it is not. Rakudo is pure compiler. Except that it doesn't compile into a file in some cases, and it doesn't compile into machine codes, into assembler, none of this. Rakudo compiles into bytecode. What kind of bytecode is actually depends on what backend is currently used, what backend you have ordered for your Rakudo compiler. The default backend for now is more VM, which stands for, of course, virtual machine, more virtual machine. This is the most developed, the fastest backend Rakudo has. We have two others. We have Java backend and we have JavaScript backend. I would say they're underdeveloped. They don't support all language features. JavaScript is not capable of threading whatsoever, simply because JavaScript does not do threads. WASM, I hope, but somebody has to do it. I would like to see WASM to be a backend as well at some point. But, you know, one of the reasons I decided to do this class and to focus on low-level things is because I hope that maybe somebody of you guys presented here may decide to join Rakudo development, and maybe somebody of you will develop WASM backend at some point. I mean, the more alternatives we have, the better. But for now, we just don't have resources. Rakudo core team is not that big to dedicate people to another backend. So at the moment, we focus again on Rakudo, and we focus on more VM implementation of Rakudo. That's the best working combination. Let's talk about the way Rakudo actually structured. I mean, what Rakudo is composed of. I already mentioned a backend, a virtual machine. This is what actually runs your code eventually. So if you execute your script, it's not Rakudo which executes it. It's more VM which executes the bytecode, which was prepared for more VM by Rakudo and by NQP. NQP is a kind of middleware compiler. It's a simplified version of Raku language, which stands somewhere in between of Perl and Raku, maybe. Not really, it's still closer to Raku, but anyway, it's much simpler, it's much faster than Raku, but apparently it's much harder to write code in because it lacks some high-level constructs we are all used and used to love. Still, we use NQP. First, it was historically done this way, and second, well, NQP is truly faster than Raku, and it's good enough for writing a compiler. And the current design is such that Rakudo cannot compile itself, actually. It's NQP which can compile itself. And when we built Rakudo, yes, this I already mentioned. Yeah, and this I will come to. When we built Rakudo, and if anybody of you tried to build it already, you'll notice that first you see more VM building, then you see NQP building, and then eventually you get Rakudo building. So those are three components of Rakudo, actually. Though each one is independent and can be used independently, but when you compile Rakudo, you can consider them as three components of the same thing. Sometimes it's easier to see it this way. But what is more important is that because all code is compiled into, all NQP and Rakudo code is compiled into bytecode, it is possible for Raku to call NQP methods, routines, whatever. Just any NQP code can be called from Raku, and vice versa. NQP can call Raku as well. We'll get back to it later in this class, but for now, just remember that there is no walls in between them. They're completely interoperable things, interoperable languages, for that matter. And actually, if anybody ever decides to implement, say, I hate this word, Python in NQP, it's possible. NQP is actually can be used to compile any language. Any language can be written in NQP, it's possible. So if you decide to write Python in NQP, no problem. You can then call Python code directly from Raku, from NQP, from anywhere. So it's, it's the basic principle of bytecode, nothing really specific here. NQP ops, yes. Often when you look into Rakudo sources, NQP sources, Rakudo sources, you may see those cryptic NQP prefixed codes, which looks like subroutine calls or function calls, whatever. They are not really functions. Those are low-level operations opcodes, for that matter. And in a way, sometimes they might be considered like a kind of assembler for Raku, but they are not. Those are pieces of code actually provided to you by NQP. But what is important to know about them is that some of them are mapped directly into bytecode operations. I mean, let me, for example, NQP object ID it maps directly into more VM code, bytecode object ID. And some other are actually implemented in NQP itself, and they provide more or less generalized view at some specific data structures or operations or whatever. So just when you see an NQP operation, just know that it's something you get from the lowest levels of the language. And if you want to know what this operation stands for, you can use those two URLs from the chat window. The first one describes opcodes provided by NQP itself, and the second one provides NQP opcodes provided by Rakudo. Again, I'm just trying to prepare you to know how Rakudo is developed, but if you don't want to focus on this, you must not. Simply just for you to know that such thing exists and it's extensively used in Rakudo code. And at this point, we finally start with the actual language constructs. And the first construct we start with is a CompUnit, which stands for compilation unit. Some developers, beginners, they meet this term when they start using Raku modules. And often the initial confusion comes from the fact that they start to associate CompUnit with a module. No, it's not a module. It's something more than a module. CompUnit is what compiler receives as its input to be compiled. I mean, in this very simple example, in this very simple script, the CompUnit is the script itself. CompUnit here starts with this pragma, use v6, and it ends after the last semicolon. And same applies if we get a module. Okay, don't look at the module content currently, but this is our CompUnit in this particular case. But this is textual representation. It's just that we know. Internally, CompUnit is a little bit different thing. Oh yes, of course. I forgot to mention this. Okay, this was pragma here. As you can see, it simply says that it's v6. It's traditional for Perl 6 naming, and because it was Perl 6, so use v6 was telling that this file is actually Perl 6. Full version of this pragma looks like this. Use v6e or use v6c. And whether you use this pragma or not, your CompUnit always starts with this pragma. If you don't use it explicitly, the compiler will insert it for you implicitly. And because, as I showed you, that Rakudo implements 6D version of language, if you omit this initial pragma, then the compiler will assume that you use language 6D, and it will implicitly put this pragma at the beginning of your CompUnit. So it's always there, explicitly or implicitly. Feels to me like I missed something, but okay, hope I'm not. Yeah, it's a bit too early. So getting back to CompUnit. CompUnit is a block of code characterized by the language version, which is a segment to it, and it's characterized by the actual code and by one more thing. And here we need to start with another subject. We shall to talk about frames and scoping. When Rakudo compiles your code, well, actually, would it be Rakudo or NQP, doesn't matter, but they compile into bytecode, they organize it into frames. I'm sorry, it's, well, another thing just to distract a little bit and relax a little bit. I apologize for any delays or confusions because I haven't had any class in decades. The last class I had was in the middle of 90s, and it was that, teaching ZX Spectrum Basic to 10, 12 years old children. So I'm rather new to this, and also I haven't had much time to train myself on this presentation, on this class. So I just do my best. So back to frames. As I told you, the bytecode is organized into frames. Internally, when we talk about more VM, I don't know exactly how it's done in Java backend, and especially in JavaScript backend. And by the way, talking about bytecode with regard to JavaScript, it's a little bit funny, but okay. I just don't have a better term for what they do in JavaScript backend. So in more VM, a frame, it's a structure, C structure actually. And the structure has several fields which are important for us here and now. It has a lot of fields actually, and it's really a complex structure. But we currently need to focus on just a few of them. So first of all, the frame has a pointer to a code object. A code object is actually a byte sequence which represents this frame. Okay, there will be an example later. You'll probably get it better. Also, it has a symbol table attached, except that it doesn't have it attached directly. There is no pointer to symbol table in a frame. It's the byte code, the code object, which has this table, symbol table attached to it. But for us, it would be easier to imagine that symbol table belongs actually to some frame. It will help us to understand some other concept without getting too much deep into all those low-level structures. A frame has two pointers to other frames. One points to an outer frame, which means lexical, or as we also call it, static chain. So if you have a frame inserted into a frame lexically somewhere, so that a nested frame can see symbols from the outer frame, its lexical relation, and so your nested frame actually has a pointer to its outer frame. And second pointer is to caller frame, meaning that we have here dynamic chain or call chain, call stack for that matter. And as I told you, there are much more other fields, but they are specific to optimization, they are specific to bouncing, other thing, whatever. We don't need all this now. Unless you go to help in developing more VM, you don't need to know all this stuff. And well, I just tried to visualize this frame representation. So lexical relation is vertical, call relation is horizontal, and so just if any one of you has better is better with visual information than with verbal or printed information, I hope it will help you to see things like more in perspective. No, I should. Okay. And at this point, it makes sense to see some examples. Okay, for those of you who cloned my repository and want to see those scripts locally, I think you can see a file name down here. You know, all of you probably know Vim, even though if you use Max. So you can get file information from here. Even though I said that I'm not gonna talk about syntax, I still have to touch a little bit of it because some structures, some syntax constructs, they're missing from Perl, for example, or from some other languages. So the syntax which might be new to some here is this kind of variable. So the sigil is nothing new to you. Scalar, it's a scalar. But the asterisk which follows it, it indicates that variable is a dynamic one. And dynamic variable in Raku, it's a variable which is resolved not lexically, but dynamically. In other words, when subroutine bus refers to variable $*foo, it expects this variable to exist in its call stack or in its dynamic chain, for that matter. So when we invoke subroutine foo do declare dynamic variable, then it invokes bar, and then bar calls base, and base should have access to this variable. But when we call bar, it will fail because bar does not declare foo. That's it. The reason of me to show you this simple example will be more clear a little bit later, because we need to understand dynamic variables to understand following example. I'm sorry. Because in this example, I use dynamic variables to demonstrate the difference between lexical scoping and dynamic scoping. So what we have here, of course. Look, when we talk about frames, the closest representation for a frame is actually a block, because block translates almost directly into a frame. But what's even more interesting is that, well, yes, we have block here, which is a frame, and we have a block here, which is another frame. And the way Raku does implement block nesting here is the outer block actually calls the inner block here. I mean, it's literally calls it. There is no any kind of inclusion, Python, so on and so on. A block here is a code object, a separate code object. And with this example, I'm going to show this to you. So lexical scoping, I think it's clear. It's clear here. So the nested blocks, the nested block can see this variable here and this variable, excuse me, and this variable here. And please ignore this dump context subroutine because it contains things which I don't expect you to know yet. So just please ignore it. It's there just to output the information I need. And also I have this disjointed block, which, as you can see, it stays outside of this block, and correspondingly it stays outside of its lexical scope, and it cannot see this variable lexically. And this line is another syntax trick of Raku. So here I store this disjointed block in a variable, and here I call this block manually. I think it's pretty much clear. And now look into the output. Because there is no easy way to distinguish one block from another block. One of the reasons why I use dynamic variables here is because when I see this variable in a table of symbols, I know that this symbol table belongs to this particular block. Okay, hopefully it's clear. And wait a second. Yes, the first output, block of output comes from this call to dump ctx. This is the first one. And what we see here, this is a frame. So the innermost frame is 0 and so on. The outermost has the biggest number. So we see that this is the inner block B2, because we have B2 here. Then we have its outer block, and then we have CompUnit address space, because CompUnit is also a frame. Actually, I was going to talk about it later, but somehow naturally it fits here. But this is lexical relation. And when we look into call stack, we see totally same structure. We see nested block, we see its outer block, and we see the top level, the CompUnit. So as I told you before, blocks are implicitly called when they used in sync context. Okay, just let's keep it for now. When they are used like this. So this block is called by CompUnit, and this block is called by its outer block. And this exactly what we see with the first block of output. But then we call the disjointed block, and it also dumps its symbol table. And when we come to this dump, which is the second output block here, we have completely different picture. Because as you can see, we have only two lexically nested frames. We have actually the disjointed block frame, and we have CompUnit frame. And this is lexical relation which we really have here, because the block is here and the CompUnit is its outer. But the call step, yes, we have disjointed, we have the nested block, and we have the outer block, and then again we loop back to the CompUnit here. So with this example, I hope this example makes visualizes two principles pretty much well. The first principle is that one frame, one block in Raku actually calls any nested block in it. Actually, the picture is the same if we do it like, if we add a conditional statement. Sorry. So over here, it's also the same. If condition is true, then call this nested block. So we always call, always. And the other concept which I hope to make clear is how the dynamic linking, dynamic chain is used to resolve dynamic variables, because as you can see, please ignore the unit marker for now. I mean, I'm not going to talk about it directly, but this is a subject I'm going to touch a little bit later. That's something interesting as well. So lexical and dynamic. Lexically, as I said, lexically disjointed block cannot see symbols B1 and B2. But when dynamic resolution is used, as you can see, they're accessible. And if we do it like this, I will uncomment this line here. And repeat. And here, when disjointed block is invoked, you see it outputs second block. This output comes from this line here. But if we invoke this block individually from the CompUnit level and repeat the script, oops. That's because dynamic chain is different in this case. So if anybody has any question at this point, I'm ready to answer it before we move on. Okay, probably no questions. So why all this is important? It's important on its own. But aside of this, it allows us to better understand some other principles of how Raku works and how it's built. As I told you, CompUnit is a frame. So when a compiler starts compiling your CompUnit, it creates a frame for it, separate frame. And as a frame, it has its own lexical scope, and it also has its own dynamic scope. For now, we're going to talk about lexical scope. And the lexical scope of any unit, we call it setting, meaning that it's a setting in which a CompUnit operates. By default, Raku installs its core as CompUnit's setting. And core is actually a kind of standard library of Raku language. I'll have a little bit more about it, but say, oops, over here, when we use say, we actually call a subroutine which is defined in language core. So it's not a statement. It's a symbol which is available for our CompUnit lexically, and actually not only CompUnit, of course, but to any code. Mm. Mm-hmm. And the next thing which worth mentioning is that core is different depending on what version, language version you have requested. Now it's time for some more examples. We are going for core settings 0 to start with. Again, I'm not showing this code to you because it's beyond the scope of this class, but still I had to do it to show you this core settings 0. The hidden code actually dumps all the symbols it can find in lexically outer spaces of our CompUnit. And what symbols does it dump? Well, you see grep here, you see say here. You probably will find some other familiar symbols here like tangents, whatsoever. So those are symbols provided to us by 6C version of core, Raku core. Excuse me, some questions. Oh, yes, I missed a question. Sorry, about coroutines, the question about coroutines. Well, basically, frame is pure technical thing. No, frankly saying, I'm not ready to answer this question for now because coroutines has a little bit different meaning in different languages. And so if you want, we can try to discuss it a little bit later if you provide me maybe with some example or something like this. We have a kind of coroutines in Raku actually. We do have them. And when you're gonna study supplies, for example, then basically that's what happens there. It's supplies are using some kind of coroutines, but not the way they're defined in other languages. So I'm probably not ready, not ready to cover this subject. So let's get back to core setting here. As I told you, core setting is available to our code lexically. So we found all those symbols. And one of the symbols provided by core settings is this constant. And this constant tells us what core setting we are currently using. So, for example, this is another dump, very much simplified, of our frames. So we start with CompUnit frame. Then we see some empty one. Don't ask me what is it. It's beyond our discussion. And then we see that the constant core setting ref contains C. C is because we requested 6C language version for our script. If we switch to 6D, then we see D, but we also see C in the next outer space. And this is what you're going to expect with 6E language version as well. So what I'm trying to show you here is that those are still frames. The innermost, which is our CompUnit, outer frame, another outer frame, and so on, so on. So basically what we see here is that 6E core setting, it's actually lexically scoped by 6D core setting, which is in turn lexically scoped by 6C core setting. And lexical, oh, it's different. Okay, I will come back to this example in a moment. For now, I want to show you this. Because text form is probably not easy to read and not easy to grasp without understanding the code which backs this output. I made this pseudocode example. So in this example, as you can see, our CompUnit is represented as a block. So this is our script. And in this script, we request for 6D version of Raku language. Apparently high volt, yes, it used to be. And since we requested 6D, our CompUnit is installed inside another block, which is actually implements 6D core. And 6D core is implicitly installs 6C as its outer. So this is the structure of our typical CompUnit, a typical script in this case. Why is this so important to understand is because when we have a feature which is implemented in later version of Raku language, but is not implemented in early version, usually this feature is represented by a dedicated symbol. Would it be routine, constant, some kind of type object, some kind of class, whatever. We include it into core, which corresponds to the language version for which this feature was implemented. And if the very same feature was implemented differently in earlier language version, then newer version would just lexically override the previous version. Like on this diagram, you can see that core setting ref is actually represented in both core settings, in 6D and 6C. But when we request it in our code, we take it from 6D because it's lexically closer to our CompUnit. Okay, hope it's clear because, you know, what makes Raku approach in this respect different to languages like C, C++, and whatsoever, the standard library do not export symbols into your space. Instead, you have lexical access to the symbols in your standard library. I mean, the difference usually is not that visible in code, but it might be pretty important at times. So it's very nice to know about this. Very useful in first place. Still, there might be a confusion about this pseudocode as well. As I told you, nested blocks are called directly by the outer blocks. So one may expect that in this case, our 6D core actually invokes CompUnit. But that's not the way things work here. If you take core settings 2 example from the repository and call it, then yes, you can see lexical outers. We already used to them, so we have CompUnit frame, and then we have 6C settings here. But when we dump the call stack, we see absolutely different picture, and we see no any core symbols here. There is no single core frame in the call stack. And I'm gonna reveal a little secret here. All the frames we see in call stack, they all belong to our compiler, actually. Just without focusing on those particular symbols and frames, what happens inside? Okay, back to this. Sorry, let me skip this page and go here. It's a little bit less information and a little bit easier to see it. So the way the compiler works, when it loads a CompUnit and finishes compiling it, it forcingly sets the lexical outer pointer in our frame structure to the frame which belongs to the core setting. I mean, its compiler does not invoke the setting frame. No. When it comes to invoking user code, the compiler invokes directly CompUnit frame. So I'm afraid I'm messing up here and cannot. So there is a way to take any frame and explicitly tell that your lexical scope will be this frame. You can do it manually for any kind of frame. And the worst case scenario, you can even do it runtime, so that your block, for example, may get different lexical scope in different situations. It's possible. It's doable. It should be avoided, but it's doable. And yeah, the same situation about core setting. But what it means to us when it comes to language versions and how it affects us? Here I have another good example. Quite recently, Elizabeth Matheson has implemented last statement with a value, which means that we can actually stop grep looping over a list of values whenever we need it. Yes. I'm sorry. Yeah, I have to switch to. Okay, now I'm really using the latest version of Rakudo. So as you can see, our output stops at number 19. This is because of this condition here. If you just avoid doing this last, you see we get prime numbers up to 47. So with this last false, we can stop at any moment we want. And this feature is only available if we use 6C. And if we switch back to the default 6D, yep, apparently we get an error here. Because 6D just doesn't have appropriate implementation of the last subroutine. Okay, and this is a file from 6E core, where you can see that new implementation of the last subroutine exists. And from its signature, you can see that it's accepting an argument. Okay, so at this point, we are done with cores and frames and so on. And so if you have any questions, I see one question. Last false. Yes, last false. The logic here is that, okay, if you remove this line, what happens? We iterate over first 15 numbers, and then we check if an element from the list is a prime number. And if is prime returns a true value, then this block returns a true value, and grep knows that the current element is accepted. Contrary, if is prime returns false value, grep knows that this value must not be included into the output. But last means that we end current block, we quit current block, and we want a value to be returned. And if we return a true value, it actually tells grep that this number is acceptable. And so you see 20 to be included as the last element, even though it's not a prime number. That's because last simply supplies this block return value to grep to be interpreted. I do false because I know that 20 is not a prime. More correct implementation would be last is prime. So it works as expected. Last true if, well, one way or another. Yeah, it might be confusing. I mean, to me, it was pretty much clear, no problem at all. But if you don't know, if you're not used to those things, it really might be confusing at times. Okay, if no more questions here, then let's move to the most advertised feature of Raku. Everything is an object. Literally, everything. Actually, if you get back to this example here with jointed block, I already started using this concept of Raku because I don't remember. Yeah, in Perl, it's not possible to assign a block to a variable, and apparently it's not possible in C, but in Raku, it's a normal thing because block is an object. So partly I have already started with this, but there are more than that. And yes, when people hear about Raku, often they start knowing it with this statement that in Raku everything is an object, just everything. It's about the same thing. I started looking at Ruby some years ago. And because everything is an object, everything can be introspected with different kinds of methods. And Raku has a vast majority of methods to find out what object to we deal with, what this object has, what properties does it have, and so on, so on, so on. But at the moment, let's start with the most basic methods: what and which. So the most simple example is to tell you the difference between those two methods. What tell us what type our object has. And it's not just tell us the type of it, but it actually returns the type object. So if you look at this line of output, you see that int here is enclosed into braces. This is typical representation for type objects or for classes. For example, if we do something manually, as full, say full, you see, we don't create an object of class full, we just report itself, and that's how it reports itself. Which tell us a little bit more information. In this case, which tell us that we have type int and it's undefined, meaning that it's a type object. Now, if you move further down of the script, we see that we initialize the variable with a number, and we repeat what and which again. And what we get here, what didn't change, because it always returned just type object. And which tells us that we do have int, but it's initialized, it's an instance of int, and its value is 42. So I use which on many occasions when I know that something goes wrong about my code, and I want to see if some object is already initialized and if it's not. And another thing about which, this long number over here, it's so-called object ID. So every object in Raku has some ID associated with it. A particular value of this ID depends on the backend. For more VM, it's this long number. Don't think of it as a memory address, because it might be a memory address or it might be not. It's not guaranteed. But what is guaranteed is that it's going to be unique for each unique object. And so when I know that something goes wrong in my code and I see different data coming from seemingly the same source, I often use which to see whether the same objects are actually coming to the problematic location. And often it helps, so that I know, for example, if I throw an event object over here, then I check it here in my code, here, and I see that it's all the same object. It has same object ID. So I know the path my event object goes through the code. Okay. But which, as you can see, which output is different for initialized values, for instantiated values. And in this example, I simply want to show you how it differs. And so we apply it to a string. And here we declare a dummy class foo, we create an instance of this class, and we report it. And again, because everything is an object, you see, I use method say to output it. I simply chain methods in one call. So we see here string is reported as string class, which has value foo, but for class foo, again, we have class name. But as you can see, there is no U in front of the object ID, and because foo is not a value object, I mean, it doesn't have any particular value associated with the object. It is reported by its object ID, not by the value. So that's how which introspection works. Also, if you get back to that example with lexical and dynamic scopes, where I take a block and store it into a variable, as I told you, it's an object, so it can be stored. And in this example, we see that if we declare a block like this, but then we call a method on this block, this block is not called. We got this block reported with which method here, but the code of this block, which should have reported as p constant, it never was called. Just, you know, to combine two subjects together, to link them to each other. And I love tricks. I mean, I don't like using them in real code, but I love tricks because they reveal some really deep behaviors of the language. And in Raku, we can find out that a label is an object too. I mean, really, everything is an object. Just everything. If we run this code, look, label instance. So the symbol full, then we use it in the say the switch and get this output. And then we ask this label object to stringify itself in a human readable form with gist method. And here what we get of this gist method. Well, actually more correctly would be to say this is the output. So you see a label object knows where it was created, line number 4. Yes, line number 4. And it knows the context in which it was created. So it keeps a number of symbols before the label and a number of symbols after the label. Okay, yes. We also have another pretty much popular introspection method, .how, but we will come to it a little bit later. For now, I think I'm done with this topic. And before I proceed further, if there are any more questions, I will try to answer them. Okay, probably not. So we have a question after all. Okay. Daniel, I think you can unmute your microphone and say your question.
I vaguely remember something in the documentation saying that variables and scalars break the everything is an object rule. Is that true, or is there anything you can say that would sort of illuminate that?
Sorry, Daniel, could you please repeat?
Sure. This may be incorrect, but I remember something from the documentation saying that the way Raku implements variables with and especially scalar variables breaks the idea that everything is an object. Am I remembering that incorrectly, or is there something to that?
Daniel, you're currently running ahead of the train.
Oh, okay. Well then, never mind. I guess we'll get to that soon.
Yes. When I get to this point, it's gonna be a lot of things to say about, really a lot. So,
all right, I'll look forward to that in a few minutes then.
Thank you, Daniel. Okay.
Vadim?
Yes.
This is Bill. I was doing which-3, and I wasn't sure whether it was giving me an error there. That little up arrow symbol. Is that not an error?
No, it's not an error.
Okay. All right.
It's,
well, I'm reproducing what you say. I just go ahead.
This label, actually, it's no wonder that you've got confused with it. When I first wrote this example, I was also thinking that, oops, it's an error. But The point is that label just uses this Rakudo Raku convention to report the place where it is located. And that's it.
I see.
I mean, all this output you see here, it comes from gist method of the label.
Okay.
This is, oh, we can do it like this. And actually, we can remove this gist because this is what say does for us implicitly. Just for information. Because say doesn't output things as is, it stringifies them first and it stringifies them using gist. And okay. So here is the angle brackets, the opening one, this one, and the closing one.
I see.
And everything what is between is label stringification.
Great. Thank you.
Yeah, welcome. Okay, meta object protocol. When I was preparing this class, I digged a little bit into the history of meta object protocols, and at some place it was said something like all languages implementing the principle of everything is an object has some kind of meta object protocol. I don't know how much true is it, but well, at least I know that the concept comes from common list and Smalltalk. And then where I first met meta object protocol was Moose in Perl, Moose framework, and a little bit of Moo, but in Moo it's hard to call it meta object protocol anyway. It's pretty much specific. Anyway, so Raku has its own meta object protocol, and it's barely standardized. It's not spec'd in Rust completely. We do have some bits and pieces here and there specifying how to use a couple of meta object protocol methods, but largely it remains unstandardized. For me as for a developer, it's good because often I can change API without worrying that it would break the specification. Though it might also break ecosystem modules, but this is being closely watched by release manager. So he won't slip any breaking changes into the language. But the bad thing is that if you use some features of mob in your code, you are very likely to be on unsafe side of the things, because API might change and your code might break. So mob is very attractive for doing different kind of things. I will show some of them later. But when you use it, be careful and be prepared that you might get some problems. Okay, enough about bad things. Let's talk about great things. Where previously I was talking about Rakudo structure, it was about the way we compile Rakudo. Now I'm going to talk about Raku implementation structure. It's a little bit different thing. Raku implemented by three major components. First is, of course, a compiler. Compiler as such, as you know, the object which takes your source code, produces, parses the syntax of your source code, and generates code for it. How it does generation, that's currently beyond this topic. Meta model which is actually the implementation of meta-object protocol, is responsible for type system semantics in Raku. Okay, yes, anyway, I'm going to talk about it. So if you don't really understand what does it mean, just ignore it for now. And core setting we already know about. It's our standard library. So example is, okay, let's take this example. So over here, when we see int, we know it's a class, and we know that there is some meta-model code which actually implements this int. But also we know that int itself is declared in the core, in the language core, in core settings. So keeping all this in mind, and of course, compiler has to encounter this int symbol in our code. It has to find out what kind of symbol is it and how is it responsible for doing things. And well, what the hell? Like int, you all know what int is. Why do you ask me, compiler, to do something about it? Yes, because we know, but you don't. You have to find out, and you have to handle it correctly. All three components are pretty much tightly interweaved to each other. I mean, you cannot pull any of them and separate it from two other components, even though those ties are not frequent in some cases, but they're strong enough for us to not be able to separate them. So again, when we talk about Raku, we basically keep in mind those three components. Meta-object protocol structure. Not the best topic name actually, but okay, let's go with it. So as I told you, int is backed by some kind of meta-object code. As a matter of fact, the precise definition would be any class, any type object, sorry, no classes here, just type objects. Any type object is backed by an instance of meta-object protocol class. And this is what we get when we use .how method. How 0. So if you look into this example, you see I apply how method to different kind of objects and type objects. The last line, just ignore it for now. And here is the output I get. So string, it's actually a class type str, and it's backed by class how. True, this might be not really expected by some, but true is actually an enumeration value. Int, it's also a class. But unsigned int, it's a subset. So unsigned int also comes as a surprise to people sometimes. And why do I have this second int here? Just by mistake. Okay, I don't need it here. And if you consider this output, we see all this .new appendix. This is how Raku default stringification in GIST tells us that in this case, we are being reported with not a type object, but with an instance of this object. Here, in other words, this suggests that at some point, class how was instantiated with .new method. To check it, I use this last line. So I use method defined, which will tell me that what .how returned to us is actually defined. Just to show you that it could be different, you int defined. So if I apply it to a type object, to a bare type object, we get false because it is undefined. And undefined in Raku means it's a type object, and defined means it's an instance of this type object. Now, let's have some fun. So, when say reports a class to us, as I already told you, it uses method gist to stringify it. But what happens inside? Inside, Raku code actually uses meta model to find out what the class name is. And this is how we get the first line here. It's .full. But since meta model knows what the class name is, then we can change it. And here is our second line of output, which is foobar. Wait a second. But I was asking for foo. But you give me foobar. That's because what we see here in code is for your eyes. And things are somewhat different internally, and later I will come back to this subject as well. So, but for now, let's just accept the fact that we can change a class name on the fly, and this change will affect our class immediately. We can rename it. We can rename the way it gets reported. This line is actually the same as this line here. It's just another syntax used to access meta model methods. This operator is called meta method call operator. What it does, it's just a shortcut to apply .how method, and by convention, most of meta model methods accept the type object itself as the first argument. So the meta method call operator does this for us implicitly. It takes the object it's invoked upon and uses it as the first argument of set name here. So it's really convenient thing, because you see, even in this simple case, it's already, two variables. We have to call how, we have to remember to pass the type object as the first argument, whatever. But what if we have something like, I don't know, .int, we convert a string into int, and then we would like to call some meta method on it. So we would have to do it something like this. For example, oh, you know, it's too much hand work and stuff like that. And what if I need not int here, but the object itself? Of course, it's much easier to do it this way. Just a convenient shortcut. Good to know because you're likely to use some meta methods in your code. Very likely. I mean, even though you're not going to do some kind of development for Rakudo or Raku or whatever, at some points you will use meta methods. Oh yes, thank you for the link to documentation. Actually, I forgot to put it here. Now, well, actually, this bullet talks for itself. The entire meta model, as well as Rakudo compiler, are actually implemented in NQP. It is possible to write some meta model code in Rakudo as well, but and this ability is used by some third-party modules, some ecosystem modules. It's especially fantastically great and so on. I don't have enough words to express it. It's used by ORM called RED, database framework. And it's used so artistically and so, I mean, it's just pure pleasure to use this framework to work with databases, believe me. And it's fully apparently written in Raku. But when it comes to Rakudo implementation, in Rakudo meta model is all NQP. And yeah, I also refer to this note I made earlier that NQP can call Raku and Raku can call NQP. So this is used in meta model. And as you can see here in this example, set name is actually written in NQP. As simple as that. And NQP itself, as I also mentioned it earlier, it's a simplified version of Raku. How much simplified? Well, it is sufficiently high level to implement the principle of everything is an object too. So in NQP, everything is an object as well. And therefore, NQP has its own meta model. And so we get deeper and deeper in this rabbit hole. This is what my next example is about. Look, first line, we get meta model object for number 42. And then we ask about meta model object of the meta model object we've got in the first line. And then meta model object of meta model object of meta model object, and so on, until the last one. You know, the house which Jack built. Gives us this one we already know about. Class how. Then we get NQP class how. This is meta model class for Perl 6 class how. But then we get some strange one, know-how. And then we get know-how again. And if we add one more how to this chain, we get no how again. So we get into infinite loop at the end. What's happening here? As I told you, NQP is capable of building itself. But first, it has to bootstrap itself. And, you know, it's chicken and egg situation where there is no clear way to create a class without having a meta model for it. And meta model requires classes, which again requires meta model. This situation has been solved by one single requirement to the backend virtual machine. It has to provide a type which is sufficient for itself. A type which has itself as its own meta model. It can do nothing except of method how and method name, as far as I remember, maybe. Both methods are implemented by virtual machine, purely by virtual machine. And then we use this class to create our first level, the deepest level meta model class. If it's not really clear at this point, don't worry. I mean, I mostly tell you for avoid any possible confusion in the future. But this piece of code I would like to show you. This is a source file of NQP compiler. And yeah, this is our first metamodel class declared in NQP. It is declared as some weird kind of thing, know-how. So if you ever get so deep in introspection, at least you won't be scared about those things. Do you need this information? I don't know, but at least you will know how to use it if you ever need it. Three examples. Okay, and I have one more example left, yes. I told you that it is possible to write metamodel in Rakudo. But it is also possible to modify a metamodel in Rakudo. Look at this example. We have class foo as our laboratory mice here. We have a role, skip it for now. And we have some say and so on and so on. The piece of syntax I would like to explain to you is this one. Does, in this context, mixes in role my how into the class on its left-hand side. So basically nothing, it's, in a way, it's something like saying, so something like this, except that we do it runtime. This is a kind of thing Raku is really great about, because you can do pretty impressive things just at runtime. Even though you have compiled code, you can modify it in so unusual ways, and it's supported and it works clearly and it doesn't fail. In this role, I define a method short name. Actually, short name is the method which is used to stringify our class. And when I mix in my role into the meta model class here, I actually override this short name. You see, first line comes from here. Then I apply the role and do it again, and I get different output. In a way, it's also some kind of trick, but as a matter of fact, this behavior is often used by many modules, and especially it is used by traits in the core and so on, so on. So if you read about traits, then keep in mind that many of them actually modify your meta model object in similar way to what I have shown you in this example. Good. So far, so good. Just a list of methods which I used most and which you may consider very useful in your code often. Name and short name, I told you about. They return full name of type object and its short name. Let's not focus on this, but let's pay some attention to MRO method. And MRO actually stands for Method Resolution Order. What it means is when we take those two class declarations where it's clear that class bar inherits from class foo, and then we ask bar about its method resolution order, this is what it gives us. It gives us bar, then it gives us parent foo, then any, then mu. This is the order which is used by Raku to look up for methods. So if you do something like bar say, what happens is Raku goes to search for say method on bar. It's not there. Then it switches to foo, say it is not there, and then it switches to any, and any has method say and. So we found the method object and we can invoke it. This is really important thing because one of the problems about C++ was always their inheritance, multiple inheritance. It wasn't really clearly specified which way the inheritance works. It wasn't really well thought out, and it was causing huge amount of problems to developers. That's why we got Java, and really, I don't like Java as I don't like any language which dictates to me how I write my code. If I want multiple inheritance, I want to have it. Raku didn't go this way, luckily. And in Raku, it was specified that we don't consider inheritance. Instead, we use inheritance to build a specific order of classes, which we then use for method resolution. And since the algorithm behind this resolution is known and published, we know exactly how our code behaves. If you want to know more about it, you can find more information on the network. You can find more information in the documentation. But believe me, quite often you may need to ask your class about MRO to find out why you get not the method you expect to get in one or other situation. And there are some other cases where you would need it. Another thing. Sorry. Look, when we declare var, we explicitly define that its parent is full. But for full, we don't define any parent whatsoever. What happens in this case? The compiler implies that any is the default parent of any class which do not have any explicit parent defined for it. So whenever you create your own class, just know that you inherit from any, and all methods available on any are going to be available on your class too. Hopefully that's as simple as that. There's no really any tricky part here. Methods. Methods actually return your methods defined on your class. There was a recent discussion, and there is an issue on GitHub about stringification of method objects. So over here, I use explicit call of name method to make things really, nicely visualized. So if you consider this example without my participation, just keep in mind that if you just dump the list of methods returned by this meta method, you might get a little bit garbled output in the current version of Raku. We look at another thing. So those the methods defined on class str. I'm sorry. And alongside with methods, meta method, we also going to be using can meta method too, which is, I think, also its meaning is pretty much clear, but its semantics is different from you might expect. Look, for UC method, yes, str can do UC, which stands for uppercase, but you see we get a list of method objects. We get two UC methods. Why so? It's because there are two UC methods. One is defined for str and another is defined on any. But for us, it is important to know that can does not return a Boolean value. Moreover, we must remember that NQP doesn't have concept of Boolean. As in Perl, it uses implicit Booleans like 1 is true, 0 is false, and so on. Defined is true, undefined is false, and so on, so on, so on. And next line, we ask for full method, which is clearly not defined. And can gives us just empty list, which is also false in Boolean context. like this. We make it Boolean. And so you can use can to find out if your class or somebody else class is capable of some method. But just remember that it doesn't return Boolean. It returns a list, and in certain context, this may come out as pretty much a surprise. The next example I better skip for now. So we have method scan. Find methods is and lookup are two other methods from the very same family, and they have different semantics. And I think it's simply too much for now. And it's time to switch to another subject now. So do we have, yeah, questions? Methods. Oh, yeah, yes, I meant exactly that issue. Dot methods. Well, Daniel, it is possible, I know, but I'm trying to use as simple syntax as possible, just not to confuse people. But yes, thank you. Good. Good. You know, when I was preparing this class and this presentation, I wrote a note to myself for this particular page that, okay, let's get some rest and change the subject. Because, you know, we get focused on one subject for a long time. It's going to be too much for our brains. We need to rest, to have some rest. When I finished this subject, I just found out that it's much, much bigger than anything we had earlier today. It's really a huge one. And everything I told you before, it was driving us, guiding us to talk to this subject in the first place. Symbols and containers. And let me use some clickbaiting. Raku doesn't have no variables, nor subroutines, nor functions. Footnote, not in the classical meaning of the compiling languages. You know how they do it in advertising, you know, big font, we do it for you free. And a little bit footnote, oh, well, with a little bit of monthly payment since a certain period, for example, whatever. So why generally this statement is not true, there is some reasoning behind it. And yes, I promised not to talk about my variable equals 42, but I'm going to talk about it. Just from different perspective. For example, I'm going to talk about it from this perspective. As you can see, I use two different segment operators here. The first one is actually a segment. The second one is called binding. Here is the example code which explains the difference between the two ways of initializing a variable. So what we do here, I assign 13 to full, we bind bar to full, then we assign pi constant to full, and then we report those variables again. Really simple. And many of you has probably guessed, even if you don't know what this binding operator is about, you could have guessed the outcome. So in a way, one can say that with this line, bar became an alias to full. So they became basically the same thing. And the rest of this topic, I'm gonna tell you what's exactly happening here and how this binding implemented and what consequences it has for your code and, well, basically for any other code. So let's start with pretty much familiar syntax to the most of you. Any language, many languages where they use the concept of namespaces use double colon for name resolution syntax. So if you group your symbols into modules, packages, whatever they call it, when you reference to this namespace from outside, you use double colon to find a symbol there. For example, in Raku, we declare a module. And remember, as I told you, that CompUnit is not a module, which is sometimes confusing people. Well, here you see we can declare a module pretty much everywhere, no problem. We just create it whenever we need it. Inside this module, we declare two public symbols. Our here stands for public, contrary to my, which is lexical scoping and which binds a symbol to a particular lexical scope. And we just resolve those symbols. Oh, easy. This is subroutine call. This is variable output. Those two lines here. But in Raku, everything is an object. And full double colon is an object too. And it actually represents the symbol table, which is associated with our module. So remember, as I told you, when we were considering frames, I told you that there is symbol table associated with the frame, and this symbol table directly belongs to the code object. So when we declare a module here, we actually declare a code object for this module. And both variable bar and subroutine bar are getting installed into the symbol table of this code object. And what happens then? We have access to those symbols via a data type called stash. Excuse me, like this. So here we introspect the full double column, and it tells us that it is a stash instance. Stash, I think it's easy to guess, it stands for symbol table hash. And if we use MRO to look into the inheritance of stash, we find that it actually inherits from a hash. And therefore, we can use a stash instance as a hash. Okay, just very briefly, .who is another introspection method, and it's actually the method which returns us the same stash. So you can see it over here. And from object ID, as I told you, I use object ID to identify same objects. So foo.who and foo double colon, it's the same stash. So use whichever one suits you best. But from syntax point of view, double colon is usually much more expressive. So we are getting back to our module full. And because full double colon is a stash, which is a hash, so we can ask for its keys. And here's what we get. Remember, we have declared two public symbols, variable bar, scalar bar, and a subroutine bar, which, as you can see, represented as ampersand bar, because ampersand is the sigil for code objects or for callable objects. Okay, and because these two lines here simply to demonstrate that stash is really a hash, because I just, take a dummy hash and also used .keys with it to see for its structure. And as you can see, we have two keys, A and B. Here is A, here is B. For which, well, here it goes, for which. You see, the reason I enclosed it into braces is just to visually separate. Because basically, this is the same. Okay, so stash is a hash, and this allows us to write this line of code. So we can assign a value to a key in full, except that anybody noticed that there is no declaration for scalar full in module full. It simply doesn't exist. Again, same output because it's the same script, but you see, it doesn't fail. Moreover, when later we resolve scalar full in full namespace, we get it. So this one here, it stands for this output. So guess what? We just created a variable manually without declaring it. And it's available. It's available for use. That's a feature of another great feature of Raku, because again, despite of being compiling language, Raku allows for a huge amount of dynamic operations, dynamic changes in its code structure, in its data structure, in many, many other things. And by the end, if we dump symbols from the stash, yes, we do see a new variable in there. Is it? What exactly is instantiation? Sorry, I just don't understand what this last question means. If you could please elaborate, I would gladly try to explain. Meanwhile,
trying to the foo, the $ foo scalar that you said wasn't defined, but you're able to get the one out. Is that instantiation? Is that just does Raku understand that you want that variable there?
no,
line 16 where you are. Line 16 where you are in this code stash 2.
I just create a new key on the stash, and
okay.
This code below, this is not an instantiation. I would rather say that it's auto-vivification.
Auto-vivification, sorry. That,
Yes.
very, very good. Thank you very
But,
much. Thank you.
Yeah, you're welcome. But still keep in mind that when it comes to this line, you see Raku does not resolve this symbol statically at compile time. Instead, in this location, it is Rakudo compiler inserts bytecode which dynamically resolves the variable. This is what makes this kind of things happen. So in a way, yes, we not only auto-verify a key on the stash, but in a way we can say that we auto-verify a variable in this module.
I see. Great. Thank you very much.
You are welcome. And let's this will come to later. Yeah. Aside of custom modules, okay, let's make it not that confusing. Raku actually has two concepts, similar concepts. It has packages and it has modules. They are very much similar, but they're still different. Package just declare a namespace. It's low-level thing. Module, it's module inherits from a package, and it does a little bit more things. It has more functionality. So sometimes I'm going to be using package word. So don't be confused. Package usually refer to low-level namespaces used for specific purposes. In this example, we have one of those namespaces. This package named global. Global is our CompUnit, primary CompUnit namespace. And when I say primary, it really means something, because there might be, I don't know, hopefully word subsidiary would be the right one. So kind of subsidiary CompUnits. If you use this keyword in another place, it would still refer to the main, to the primary CompUnit. Let's see. First, the simple case. So at this line, you see again, I dump keys of this stash. And what it gives me class full, and it gives me hash percentage. Because here we have our hash, and here we have our module. So far, so good. But here, let's complicate the situation a little bit. I introduce a module which is defined in a separate file. And look, I also define a variable in this module. Then I declare the module itself. And then I declare a subroutine which would dump this global namespace for me. And what I get, I get the same global as I had in the previous example. So when you ask for global namespace in your module, you actually get it from your script, which consumes your module. Okay, but then we have globalish. Globalish, the name means that, well, it's kind of global, not totally. And globalish is our modules, CompUnit, namespace. And again, don't mess it up. It's not modules namespace. It's the namespace of the CompUnit where our module is defined. That's why we see this variable module sorter and /4 the symbol module sorter and /4. It's a way for simplicity. Okay, you remember that if we declare something as our, it becomes public in its namespace and it should be available on the stash. But as you can see, we still don't get it in the output because again, it's not globalish, it's not CompUnit namespace, it's modules namespace, and we don't dump it. Global has one unusual specific, actually. Let's modify our script. Global. Nothing really confusing here. As I told you, we just create a new variable in the global namespace. Good. So guess what? We get a dynamic variable. The point is, any variable declared in global namespace is accessible as in the dynamic scope of any module, any code we use in our application. This is pretty much obscure thing and not well documented. So since I'm telling you all this tricky stuff, I have to warn you that if you're gonna be mangling with global, you better not. Just better don't do it without clear understanding what exactly you do. Because this might have some very unpleasant side effects. For example, you can create a variable on global, and some module you use in somewhere inside is using the same name variable just by accident. You know, simple semantics, simple names. Well, just inside it, and somewhere this module is expecting the variable, the dynamic variable, is to be uninitialized, and then it accidentally finds it initialized. Kaboom! Problem. And really, it's a kind of problem which is very, very hard to be traced down. We actually have another namespace for this purpose. We have process. And this namespace is, yeah, I think it's process. Yeah. This one is documented. And its behavior is also well documented. So if you need to create a custom dynamic variable which is accessible globally, then do it in process namespace in first place and well document this behavior. everybody must know that you use this variable in your code, because still it's not safe. Still there are clashes possible. Aside of stash as such, which represents real packages and real modules, Raku has a set of pseudo packages or pseudo packages. Those are really useful for introspection. For example, my. It's the simplest one. My gives you symbols available in your local lexical scope. And when I say local, it's really your innermost lexical scope. Look at this output. We have buzz and we have $_. This one is implicitly defined for us by the compiler. So here is buzz variable, but no bar, because bar is our outer scope and my does not see it. Well, it looks pretty much useless at this point, but it has some use. We'll get back to it later as usual. Let's introspect this pseudo package and let's see what is it. Oh yes, it's a module. It's a module. So as you can see, my is also a type object because it has a meta-model representation for it. And my double colon is a pseudo stash. Pseudo stash is an object. Oh, and I forgot to provide you with MRO. Okay. Pseudo stash is it's not a hash. I forgot. It's a map, but one way or another, map class is immutable version of hash. So don't be really confused. Think of it as a hash anyway. Pseudo hash is different from the stash. Oh, pseudo stash is different from the hash because depending on how which flags were used to create an object, an instance of pseudo stash, it will collect and provide you with information about symbols available in certain namespaces and in certain conditions. It's an extremely powerful tool for introspecting symbol terminals. Good. For example, caller, it's another pseudo module. And caller tells you, provides you with namespace of your caller. Well, actually, the name tells you about it. But what is more interesting is that we can chain pseudo modules one to another. So here, the semantics of this line is give me my namespace of my immediate caller. Here's the symbols we get in if and din. And we get them because bias is called over here. And in my scope of this condition, we only have din and we have inif variable. So using pseudo modules, you can find basically any symbol in related scopes. Would it be lexical scope or dynamic scope, whatever. Like, for example, we have lexical pseudo model. And lexical gives us symbols lexically visible. And if you look at the output of it, okay, skip all those special variables pre-installed by compiler. But lexical also can see foobar. And foobar is actually defined here. So what happens here is that lexical traces the lexical scopes of this call site and collects symbols available over here in this scope. Okay, you can ask me why bar is not here, because really, because you can see it's not here. I must admit I don't know exactly. Unfortunately, when I was doing this example, I got a little bit confused and we need to clarify the exact meaning of lexical. The documentation says that lexical returns dynamic symbols. So this variable must not be included into the output. But unfortunately, we do get it. And my understanding of lexical is that it must return all symbols lexically visible in a particular scope. So bar should be visible, but it's not there. So it's just a new bug I discovered, like, before yesterday, maybe, I don't remember. And I will probably have to address it later. Still, anyway, you have it. And at some point, it will work exactly as it should. Do you have any difference? Yes. Pseudo stashes behave a little bit differently in different language versions. Until 6D, there was some glitches in pseudo stashes implementation, which I addressed in 6E version. So have a look. This is what I get when I run my code under 6E, and this is what I get when I run it under 6D. You see, we are missing lexical, actually missing one symbol, more than one. So when you work with pseudo modules and pseudo stashes, just remember that 6E is different. And the interesting thing here is that those are even different classes. So the pseudo stash in 6D and pseudo stash in 6E, they're different classes too, because they were too drastically changed to implement all the changes in one class. Okay, let's skip this one. And let's skip this one. I mean, those two examples I tried to show that my in CompUnit compare it to the global namespace. Sorry. Спасибо. Just as you can see, global and globalish doesn't have any symbols, but my has, because my treats CompUnit a little bit differently. Let's not focus on it. Okay, yeah, just a few of other pseudo modules I haven't mentioned. Outer, dynamic, and there are some more. And here is documentation page, which will provide you with all the pseudo modules available in Raku. Script. Okay. Containers. So before moving on to containers, let me just summarize a little bit what's been told. The whole section is dedicated to symbols and symbol tables. And basically, what I tried to show you is that Raku compiler operates with symbols in first place. So it doesn't work with values directly or whatever. Compiler knows about symbols. So what about values? And what exactly happens in this example? Yes, of course. It doesn't make sense here. So, as you can see, when I assign a new value to full, it gets assigned. No problem. Bar is bound to value 13. And when I try to assign to bar, I get this kind of error. If we take this simple example, we declare a constant and also try to assign to it, we actually get the same error. And this one is clear. Okay. So, as I told you, compiler works with symbols. The semantics of this line, we take symbol bar and we bind it to number 13. So basically what we get here, we get a constant $bar. So it looks like a variable, it looks like a scalar, but in fact it is constant, it is immutable. And the similarity of the errors reported to us indicates this, this situation clearly. And here is why. Let's consider a new introspection method, .var. We take these declarations here, one scalar, one bound symbol, an array, and a hash. And then we use .var on them and report its name. And also we report it without .var. This one. We got this kind of table. Scalar int, array, hash. So what is .var? The most simple explanation of .var method is the method provides us with the object which is bound to our symbol. For bar here, I think it's pretty much clear. Bar gets bound to an integer number, and this is what we got in the first column. We got int as class name for this object. Then what is scalar in the first line? Okay. Scalar is very much special in Raku. It's a container class. It's a class, instances of which are responsible for storing values. What is the difference? As you see in this example, the difference is what is your symbol is bound to and how you access a value. So when we access a value which is bound to bar, we get directly to the number because it's binding operation used. But with foo, the sequence is a little bit different. The code generated for you by compiler first accesses the scalar object, and then it pulls the value 42 from an attribute of this object. But everything is done totally transparent. Three. Okay. The cap signals, it's because I'm calling a meta method name. Because if we need to know the name of the class which is on the left-hand side of this operator .cap, then we ask meta model about the name. So basically the foo this would be the full representation of this shorthand form. Oh, okay, I feel like I lost track a little bit, and I'm afraid it's not really clear. So back to the scalar. Again, as I told you, there is no easy way to get a hold of the scalar object. Raku does everything to hide it from you. So, for example, what is this line here is about? Well, kind of a symbol assignment, isn't it? But in fact, the sequence of actions taken here to implement this declaration is: first, a scalar instance is created for you. Second, that scalar instance is bound to the symbol $bar. And third, value 42 is put into the scalar instance. So remember that click button headline unused in the beginning. There is no variables in Raku. This is true because a variable in Raku is a compound thing which is represented by a symbol in a symbol table and by a scalar instance. And being put together, they create a variable, because as soon as we replace a segment here with binding, we get not a variable, but we get a constant. And same actually applies to some other kind of classes in Raku. As you may remember, when we were dumping symbols earlier, I mentioned that ampersand is the sigil of a subroutine. So a subroutine, from the point of view of Raku, when we make a call like this, it translates into find symbol ampersand foo, get a code object this symbol represent, and invoke this code object. So where you say that foo is a subroutine, actually, again, we deal with two entities. We deal with a symbol in the symbol table, and we deal with actual subroutine object, which is created somewhere. And because scalar is so much elusive, the only way we can find out about it directly is by revealing the symbol. What is our symbol in the symbol table is bound to using the bar method, as I already told you. So this example pretty much summarizes those details. So value, but it's scalar. Then we bind bar, and still we get value, but this time it's bound to integer. And then we rebind again, and well, it's rebound. We got it. Yeah. Okay. At this point, the last thing I have to tell you about is that remember about the error in this example where bar is bound to 13 and we try to assign it to get a failure. Because the assignment operator in Raku, it expects the thing on its left-hand side to be a container. And we have actually three kinds of containers. Scalar, which I'm focused on right now, but array and hash are containers too. And it makes things like this possible. And well, binds directly to it. Okay. So I have a feeling like I failed to be really clear here because subject is might be somewhat confusing initially. It may require some time to, get used to it, to grow upon it. But for now, if you have a question, anybody of you? Okay. Oh, it was a bit too fast. Okay, I hope so. So I already mentioned that the compiler deals with symbol tables. And here I'm going to do some little fun again, because it's getting boring. So a symbol can contain any symbols, actually. A symbol in the symbol table, because it's a stash is hash, and hash does not provide any limitation on what kind of keys can be stored in it. So we can do many different things with them. Nothing really new here. Yeah, before having some fun, we have another subject. We have to better look into how symbols and containers are related. So if you take this example here, again, I declare a subroutine, and then I see what symbols are available to me. And I see that foo is here declared. It's no new to us. And then we use foo not as a subroutine to be called, but we use it as a symbol. And we introspect this symbol. And what we get an instance of sub with an ID. And then we refer to our local namespace and pull out the symbol out of it and introspect it. And of course, we get the same object. So these two lines simply show us how a symbol we refer to directly in syntax is related to a symbol stored in a symbol table. And then just different ways of using that symbol. We can just mention a name, and the compiler knows that if we use a bare word, that it's not a type object, not a constant, then it's likely to be a subroutine to be called. And so it calls it. But then we can be explicit and call it directly. And well, it has the same effect. But then we can do it like this. We can pull a symbol from the symbol table and call it. And while this particular form itself is not very much useful, but when it comes to indirect invocation, we can use the symbol table this way. And so our code may not know what exactly is stored in this name. It just tries to pull out a subroutine and again call it. And there's 4 ways they are same. And why they are same is because whichever approach we use, we end up with a sub-instance. And actually, when we call this instance, we can use a dot. This is actually the full form of invoking a callable object. It's kind of, calling a method braces on our subroutine object. And also, this is pretty much clear because symbol is just bound to a container. When we pull out a symbol directly from the symbol table, we can use it as a container. We can assign to it, and it works. 42, 42. But we also can do pretty much illegal things. So don't mind the code below this selection. This selection is understandable. We create a subroutine, we introspect it, and then we call it. Okay, not before I explain later. But then we do something pretty much illegal. I create a variable, basically I create a scalar. From now on, the word scalar would be more appropriate to the context. And I bind this scalar to ampersand full symbol. So I effectively override the symbol with different object. And then I introspect it, and I try to call it. And what I get, those 3 lines are coming from the start of the script. So we have a subroutine, and when we call it, we get some output. But after binding this symbol, subroutine symbol, to a scalar, this is what we get. We get a value 12, and we get it from here. And look, I referenced it as a subroutine. And then it all ends up with an error, and the error comes from here. Because full is not a subroutine anymore. Symbol ampersand full, which Raku compiler expects to be a callable, turns out to be a scalar, and the scalar cannot be invoked. And this is what the error message tells us. And I will get back to this error message later because it provides some useful information for us too. So what this example gives us? It gives us clarification of the fact that compiler, again, it doesn't care about what is symbol bound to when it interprets it. It just takes a symbol and tries to use it the way we ask it to. Because here, it's us who asks compiler to invoke this subroutine, even despite the fact that this symbol is not a subroutine anymore. And now, just some fun. And really, just don't tell anybody I saw you this example. It's terrible, but it really helps to understand how things are working in Raku. Our is another pseudo module, which represents public symbol table at the current scope. And then I create a symbol with this terrible name. And believe me, there is no syntactically clear way to reference this symbol other than use it as a key of a stash. And this is what I do in the second line. It's 42. So, as somebody mentioned, noticed this unit marker earlier. This symbol does exist in our namespace, but because it's a legal symbol, we cannot accidentally reference it from our code. And basically, it doesn't have any value assigned to it. It is used internally by the compiler for compiler needs. That's it. So the symbol exists, but it's useless for your code. But it's okay to have this symbol because really, again, symbol tables don't care about the exact symbols used in symbols. That's great. Exact characters used in symbols. Good. This is, in this example, with this example, I would try to show you another property of container, of scalar container. It actually can contain any value, any object, any type object. A scalar basically, in general, doesn't care what it holds, which means that a scalar can contain an array as well. And this is what we have here. And look at the output of the script. When we introspect foo, when we print it, we have the same result as when we print an array. But when we introspect what the symbol is bound to, we have a scalar. And in second case, here, we have an array. But really, when we use those two symbols, there is no big difference which one we use in most of the cases. So if we need to reference an element from the array, we can do it like this. And here we get but there is a difference. Let me introduce you to one more introspection method, .raku. The purpose of this method is to stringify your object in a way that it could be evaluated back into the same kind of object. So .raku actually provides syntactically correct syntactically correct representation of the object that is applied to. And well, as far as I remember, yes, DD uses Raku. But the point is that DD simply dumps an object for you instantly. And for the purpose of my examples, I wanted to prefix the output with some meaningful information. So that's why I use .raku. But yes, DD is the fast way to dump an object. That's correct. Good. Why Raku? What it gives us? Just one symbol, one additional character in front of the array we get, $sign. And it's actually syntactically correct construct. Say, you see, yes, it is accepted. What does it mean? What difference? The difference is this scalar. This situation when some kind of iterable object, iterable, I mean some kind of object which has many values and we can iterate over them. So when an iterable object is stored in a scalar, in Raku we call it itemization, because on certain occasions, which I'm going to tell you about, if an iterable object is itemized, it is considered as a single object, not as an iterable one. Okay, let's skip this one. In general, I hope it's clear to understand, and let's move on directly to why itemization is important. So again, we assign an array to a scalar. And here I'm going to demonstrate its so-called single argument rule. This is not something we have in Perl. This is something we haven't had in early versions of Perl 6. This principle which came later when a lot of problems was encountered with previous approach to iterable things. The single argument rule means that constructs like for do not iterate, they only take one single argument. And if this argument is not an iterable, then they don't go inside, they consider it as a single element. What it means in this example is here, for takes an array. Array is an iterable. And foo is a scalar. And scalar is what for gets. And so it's going to be considered as a single. Which one? 8. You see, the first 4 iterated over an array. Each line is output of this statement. And second 4 over a scalar, we've got one single array here. Really, this is kind of problem people quite often come asking about. And many newbies stumble upon this principle because really, visually, well, as I shown you to you before, when you do say $4, you get an array. There is no visual distinction with say at A. So people expect them to behave the same, but they don't. They don't because because of the itemization which taken place. Just let's make it more explicit. So in this case, it just explicitly itemized the array on purpose, and the outcome is the same. So before you, if you need to iterate over an array stored in a scalar, over an itemized array, you need to take some special methods, and we'll get back to it a little bit later. Maybe in this next example, let me check out. Yes. Why is this important, and what kind of problem did it solve? Let me modify the array a little bit. Look at this change. Again, yes, that's the thing which I forgot to tell you. So previously, this array would be flattened down, and the output would be 1, A, B, 2, 3, which is not always what we want things to be. If you need things to be this way, you have special measures to flatten down this array. But if you need to iterate over it as is, then itemization is the solution. The thing I haven't told you about is taking place implicitly. Raku itemizes this for you because by default, every elements of an array are itemized as scalars. Scalar. Scalar and scalar. The first one is just integer, and the second one is an array. But they are both itemized. Okay, how do we iterate over an itemized array when we need it? There are different ways. First one, the most straightforward one, is to turn it into array explicitly. We just prefix it with array symbol. Second way, we can turn it into a list. List is just one of the type objects in Raku. Basically, it's immutable kind of object. Oops, sorry. And the last one, we can simply strip out the container. This operator here, it is called decontainerization operator. And what it does, it throws away the scalar and returns the value the scalar contains. So what output we get? It's a straightforward approach, converting to a list, and decontainerization. And before we use decontainerization, as you can see, I'm trying to introspect it. So first, I tell you what's in the scalar foo, and then I try to introspect what the decontainerization operator returns to us. So first case gives us a scalar as expected, and second case gives us an array, just plain array. This approach is barely known by many raccoons, but it's very much effective. Okay, this script is somewhat complicated, but I tried to measure how fast each approach is. So I tried to measure how much time decontainerization takes comparing to converting into a list, and to using and to provide you this clear example. Yeah. So decontainerization, converting into a list, and truly, I don't know why, but converting to the array is the slowest one. Probably, okay, I wouldn't be guessing why. But so as you can see, the decontainerization operator is the fastest one. And for this reason, I pretty much recommend you this approach. Dot values could be, but dot values might turn to be even slower. So I can't tell you immediately, but I think it's going to be slower because still it would involve creating new objects under the hood. I don't remember what is the difference between small list and big list. The big list is a coercion method, one way or another. But what does the small list? I don't really remember for the moment. I need to refer. It's not that often as I use it. Good. Okay, a little bit late for this example. I have already told you that array by default itemizes its values. This example is about a little bit different thing. Why people are getting confused about the single argument rule when it comes to loops for in particular. Look, pretty simple situation. We create an array of numbers from 1 to 10. And then at some point in our code, we store another array into one of its elements. Sorry. And then we want to iterate over this element. And apparently what we get this array back as a single element. So for doesn't really iterate over it. You can agree that this kind of code is pretty much common everywhere, and therefore people quite often stumble upon this situation. So whenever you need to iterate, first make sure that you have something iterable. And this will spare you a couple of hours of debugging. Yeah, just another example of using the containerization for this purpose. Actually, besides of being pretty much performant, the containerization also convenient in a way that it lets us to, with decontainerization, we don't need to be worried about do we actually got an itemized thing or pure object. Because if there is no container, the containerization will return you the object itself. Yeah, you see. 30 here is a constant. And so when we decontainerize a constant, we get a constant back. So this is also one of the most safe approaches for cases when you know that we will definitely need to iterate over any iterable. Would it be containerized? Would it be itemized or not? Okay. Yes, you remember I mentioned to you earlier that list is immutable. Here is plain list as we created usually. So it's a list of elements. In this case, I wrap them into braces because otherwise Raku will try to interpret them as individual values and will try to, and will only assign one is a variable here to the scalar. So with braces, I tell Raku that it's single list object. And I would like to be explicit about it. So then I introspect it just to make sure that we've got a list, and then I try to assign into the list. And Raku tells us that, oops, guys, it's immutable. You cannot modify it. So far, so good. But let's do things a little bit different. Let's include a scalar into the list. This is where the scalar is bound to. And we are assigning to this position. We are assigning pi constant. And that's what we get. We get pi in this position. So does it break the principle of immutable list? Not really. What happens here is again a kind of symbol and object thing, because we can consider a list as a table of indexed symbols. Here, symbol 0, symbol 1, and values are bound to those symbols. So at this point here, we take symbol 2 from a list and try to assign it into it. And this symbol is actually bound to a scalar, and the scalar itself is writable. It's mutable, and therefore we get no error. So we cannot pull out the scalar out of the list. Neither we can bind into it, because list is immutable. So when we attempt to bind into a list, we get an error. We cannot modify it, and bind operates directly on the list itself. But at this point, we operate on a scalar, which is stored in this list. And well, I hope that this part is not going to be confusing to you anymore, because really, I had to push through this behavior for list, and for map. Map is actually an immutable hash. And I had to do so to fix a problem with exporting symbols where map is used. And so we needed to decide that we need to break this previous behavior where list was implicitly decontainerizing things. You know, in early versions of Rakudo, at this point, the list would strip off the scalar of $foo, and it would store just plain 42. It's not anymore. So the list is really immutable, but you can store this immutable thing into the list, and you can change this thing. This is one of the principles which also might be confusing at the beginning, but when you get used to it, it's clear and pretty much understandable. And actually, if you need fully immutable thing, you can find among third-party modules and limitations of tuples. Sorry, what was the second name? Sorry. Anyway, so tuple is different from the core list is exactly because it implicitly decontainerizes objects which it gets. So it's truly, kind of truly immutable, so on. And I think at some point in the future, we're going to include tuples into the core of Raku, but it's not there yet. Oh, yes, this example is in here. It explains why we can assign PI into second position. So as you can see, first I introspect second index on the list, then I introspect $foo, and it's the same scalar. Just consider the object. Okay. Okay. Anyone with any questions so far? Yes, based on this module. Yes. I mean, it's not a high priority task, so it's planned to be moved into the core. But since no, big demand on this, it's been postponed. Good. Just have a feeling that I'm missing something, but okay, let's move on. At this point, you might notice, if you didn't know this yet, that Raku is a language doesn't have references. It doesn't have any concept of references. And this raises a question. Since there are no references, arguments are always passed by value. How do we get writable arguments, modifiable arguments, and things like that? And the answer actually containers. And the way it works, it's still related to all this symbol object relations I was talking about lately. So let's take a very simple example with subroutine foo, which takes an argument, which I'm gonna introspect. And remember, I was talking about NQP ops. I use NQP object ID here explicitly instead of using which. And I apologize for using this kind of low-level things here, which is really beyond the scope. But the problem about scalars is that which method on scalar reports the same object ID for in certain situations. So it's going to be two different scalar objects, but the object ID they report are going to be the same. So just this is the kind of issue I also stumbled upon recently and still trying to figure out whether this behavior is correct or not. So object ID would tell us exactly the ID of the object it's like this. Okay, back to our example. We have two different calls to foo. We pass, we call it with a constant, and we call it with a scalar. But when we introspect the argument foo receives, it's always a scalar. One way or another, but we get a scalar. Each time it's a new one. So what happens here? Raku passes an integer object, but then it wraps it into a scalar and binds the scalar to the argument. Here, Raku takes a value from a scalar and wraps this value into a new scalar and binds it to A. Just so, as you can see, object ID for bar scalar and for the argument are different, which actually means that the value in bar from bar was re-encapsulated into a new container. Okay. What if we try to change the argument? We get an error. We get an error because because by default, Raku follows the principle of functional languages. Arguments are immutable. Unless we explicitly ask it to create a readable copy of the argument for us. And if we don't do so, we are immutable. Okay. But good. How much immutable are they? Well, basically the situation is the same as with the list. So if we take an array of some kind and supply it to a subroutine which takes a single argument, so we will get an itemized array, but elements of the array are still readable because what we're interested in is the array itself, the array object. And the array object is immutable, no problem here. And so, we've got an array in full, but the array is itemized. This is clear from this line. But then, no problem with assigning a value to 10th element. And we can compare it to bar, where we expect an array. Actually, to be correct, this construct, syntax construct tells us that we expect a positional. But for now, this is not important. And we also introspect the argument, and we are seeing to the 11th element. And then we report 10th and 11th elements before and after the subroutine calls. Again, it's the same. So here is argument introspection from bar. Yes, we've got an array, but the thing is, it's also mutable array. So the two elements we modify, they were 10 and 11 before. And after calling both subroutines, we get strings in them. So basically, things are simple. But then we have two modifiers for the arguments. One is row and one is RW. Is it right? They are similar and they are different. They both allow us to modify a scalar. For example, let's tell the compiler that we want our argument to be a read-write one. Basically, from the point of view of the compiler, oh, I'm sorry, it's a bit. Yep, sorry, let's postpone right? I just missed one example. Let's start with isRow. IsRow means that we ask compiler to bind our argument symbol directly terminology. Again, terminology. Let me correct myself and change terminology a bit. There is parameter and there is argument, and often they are interchangeable. I use the terminology in which, and basically Raku uses the same terminology, in which this is a parameter. So the symbol which we declare in subroutine signature, it's a parameter. And what we pass into a subroutine is an argument. So I would like to avoid this confusion, and I'm sorry for using wrong terminology. So back to isRow. Using isRow, we tell the compiler to bind our argument to the parameter symbol directly. This is why it's row. Let's see how it works. First, we take a scalar, we introspect it, and then we pass this scalar into full, and then we introspect it again. And you see, here in full, we try to assign into parameter. So I think the outcome is pretty much expected. The scalar, which is our argument, and this is the same scalar. Again, we called it argument. Okay, so parameter is the same scalar, as you can see. Then we assign 42, and when our subroutine is done, $v contains 42. So we operate, in this case, we operate on exactly the same scalar, and we can modify it. And this is how proper use of symbols and objects helps us avoid using references. So instead of passing a reference, we're still passing a value, but the value is a container. And this container has the value we are interested in. And we can modify this container. And all of this without any kind of references. And I think anybody of you who ever was writing in C knows how dangerous references are. So we just don't use them here. And I must admit that in Perl, passing values by references was also not my favorite kind of thing. It's not always easy to remember when you have to pass a reference or when you can pass a value or whatever. It's all pretty much confusing. In Raku, you just know that what you pass into method, into subroutine, whatever, is an object. It's always an object. And it's not passed as a copy. You just get the same object on input and same object on output, except for the cases when you don't care about the container and only about the value. Well, then you get this object just in a container. So the rest of the script, the end of the script, we try to pass a constant. And as you remember, our parameter is row, so it binds to this constant. And apparently, when we try to assign, we try to assign into a constant. And of course, it throws. So as you can see, when we introspect the parameter, we get a null, which is actually PI. And then it dies. So this is our one way to have writable parameters, but there is a better way. If you know that you need a writable, really writable parameter, it means you need a container. And when you tell the compiler that this parameter should be a read-write one, we tell the compiler that we expect a container here. The difference is how we get the error reported. Look, in the previous example, the error location is line 5. And yeah, we go to line 5 and well, it's pretty much innocent. Okay, here. It's pretty much innocent. Nothing wrong here, seemingly. But then we have to trace back and see that it was called on line 16, and there we might probably notice, oh, might probably not. When we use RW, the error message changes, and it's more explicit about what kind of error happened. So it really we expect the writable container. And it also tells us, well, line 3. But line 3 is our subroutine signature. So it's easy to understand that something wrong about the argument. Then still we have to trace back to line 16 to see where it happened. But well, anyway, it's already much easier to spot the issue. Because, okay, this is rather simple subroutine. It's easy to see what and where and so on. But imagine that this subroutine calls a method, and the method calls some kind of callback, and the error happens in that callback. And tracing all this chain of events, it's going to be really some kind of pain in the neck. So we better cut off this kind of issue as early as possible. And RW is one of the ways of doing it. And again, as you can see, it's all about working with symbols and objects separately. That's the whole topic I'm talking about for about, well, really long time about. Right? Compiler always knows about symbols. And only when we ask it explicitly, like in this case, that we want something writable, it takes a special action and makes sure that the object we get is actually a container, something writable. So the simple question then, why would we need row? Row is often used for low-level operations when we need to deal with type objects. So instead of saying foo of p, we can do it something like this. And then foo can operate on this type object that received if it needs to. And type object is passed as is without any containerization or any other expensive kind of operations. So this row has its own usage, but yeah, it has to be carefully considered. Just a little bit of syntax to This is another kind of sigil in Raku, and this sigil allows us to create a sigil-less symbols. Oh, I'm sorry, I have to answer this call. Okay, my deepest apologies. Some kind of calls I simply have to answer. Okay, so back to, I think, could somebody please say something? I think my earbuds discharged. Hello? Yeah. One thing after another. Okay. Switch over to other ones. Okay, good. Back on track. Once again, I'm very much sorry about all this. So how much, whatever fun could it be, but really a sigil which allows to create a sigilless variable, that's our sigilless symbol. That's a little bit of a paradox, but still. Backslash actually equivalent to this notation. And in a way, it's all three are basically the same, except that here we have to use a sigil, and it's not always what we want. So just for you to know, there is no any specific in this. But most use backslash has actually in declaring subroutine parameters. Because when we see a parameter like this, we know that it's a row one. And so this notation will not confuse us. Though again, using of isRw declaration would be more correct because we do expect a container, but for an example, that's okay. That would be nice. So no surprises. We pass a scalar, it gets multiplied by 2, then we pass a constant, and we get an error. But this sigil has another use. And this time is also pretty much useful on certain occasions. We can create aliases. And in this example, as you can see, I create an anonymous class. It doesn't have a name, but I create an alias for it. And then I can use this alias for whatever purpose I consider necessary. So we can call a method on it. We can ask for class name, and we get this auto-generated name. And we can create an instance of the same class. And then again, the class name is pretty much weird because we haven't specified a name for it, so it was auto-generated by the compiler. But here in the code, we can use it named, and we know what it is. We can give it some meaningful name, because foo, means nothing, but if we need it, we can give some meaningful name. So backslash as such is very useful symbol. Time for advertisements. Have you run any advertisements already? Okay. When I get tired, I get too serious, unfortunately. Okay. We spoke so much about parameters here already and scalars, and apparently we missed the point about type checking. But because there is no really hidden things in type checking, I would like to mention just one detail. Another statement one can hear about Raku quite often is that Raku uses graceful type checking. And what people usually interpret it is that it's possible not to do any type checking at all. And similar to the clickbaiting headline, it's almost true, but it's not completely true. It's almost true, it's also almost false. Let me just show this to you and explain what exactly happens. So we have a variable, and apparently we can assign any value into it, any kind of value. It doesn't care. You see, no error, no output. That's just work. One step further, and we add another variable, and this time we would constrain it with to be integer. And let's introspect it. Okay, one more method, and this method of is a scalar method, and it tells us what type this scalar is constrained to. Let's have a look. We have int and we have no. So int is expected, and no, well, it's something like we saw it before, but it's really something new to us, as a matter of fact. Well, at least in the context of this class, which is new. The next thing I do, I ask what parents our integer type has. And I ask for all parents, not just immediate ones, but I ask about all. And what it tells me is that it inherits from all, it inherits from any, and it inherits from no. No is the root of all classes in Raku. It's, it's like the ring to bind them all. Because whenever you create a class, as I told you, without any parent, it inherits from any, and any inherits from no. But we also have one specific data type called junction. And junction, as far as I remember, is the only type which inherits from new directly. All others are inheriting from any. So what is so special about mu? Oh, no, not now. Mu accepts everything, literally everything. Let me remind you about NQP and meta model. And for example, if you remember, when we asked about meta object of meta class, it told us that it's an object of it's an instance of NQP class how. What if you encounter this type object in Raku? How do you handle it? Because it belongs to completely different type system. Well, you handle it with mu. Even though mu does not inherit from NQP class how and NQP class how does not inherit from mu will match. And so if you create a subroutine, and then you do something like int. Oh yeah. What? NQP class how? Okay, again. Yeah, like this. And as I told you, NQP class how has nothing to do with mu whatsoever. If we try it like this, oh, it's even better. Ah, yeah. Okay, so I can't even ask it about its ancestors. It's in row because it doesn't have it. It's too low level, but still, well, I just know it's not there. And okay, let's have another fun. It was once asked long time ago, somebody asked if it's possible to create a class which wouldn't be inheriting from mu. And you know what? It's possible. Look, I have created a class which doesn't have parents whatsoever. It has a name, that's from another. So first two lines is what we're interested in. This class has a name, bool, like it's a scary one. But yes, of course, I used meta model to create it. And if you want, you can have a look into the code, but I specifically made it one line so that it doesn't bother us with details. And again, I have a scalar, untyped scalar, which is actually typed as mu. And I can here I still can create an instance of this pretty much, strange class, and I can assign this instance to this scalar. No problem. Is my class a null? No, it isn't. That's here. Just a little bit of black magic. So, once again, Raku allows you to do a lot of things, really a lot. Of course, doing the things comes at some price. So before doing some kind of black magic, always think twice whether you need it or not. And like in 99.99% of cases, really, you don't need it. But sometimes, really sometimes, knowing those steps are really helpful. Just one advice for those, when you do something like this in your code, do it neatly, wrap it, and document it. So outside, nobody must see it. You must well document some method, how it behaves, so that no surprises to people around. But just be careful. Any questions? Oh, yes, Daniel. Truly. Mu is not a kind of type which is often used in Raku. Most of the time, subroutines, methods, and other kind of code objects, they expect any. So be prepared that if you work with low-level types like meta model classes or some other direct children of Mu, expect that Raku would be exploding with type check errors. And a good note from Doomworks. I just shown you that junction is the only class which inherits from Mu directly in Raku core. But the junction also has another specific in Raku. When you use it, it is possible that you have a junction with many values. Please go to the documentation and read about it, because I'm not going to tell you what junction is. It doesn't matter here. So it is possible that when you pass a junction into a subroutine, Raku will automatically split it in those values you have in it and call the subroutine in different threads in parallel to speed up things. It happens automatically and it's called auto-threading. Sometimes you may want to get a junction, and in this case, the only way to do so is to declare your argument as having type Mu. In this case, Raku will pass it as is, so you get bare junction without any, special processing on Raku side. Good. Last kind of container we have for today, and we're gonna have some fun when we're done with this container. Proxy. Anybody of you who works with JavaScript is familiar with proxy in JavaScript. It is basically the same in Raku. The purpose of proxy container is to intercept store fetch operations and invoke your code when they occurs. Yeah, it might result in side effects. So first, let's consider, as usual, let's consider some basic code. here. First of all, notice that I use binding here. To avoid long explanations, just keep in mind that because proxy is a container, you cannot simply assign it into a scalar. You better bind it to a symbol. Very modern JavaScript, yes, very modern. I'm trying to avoid any old versions of JavaScript when I work with it. So when we create a proxy instance, we feed it with two named arguments: fetch, which has a callback for fetch operation, and store, which has a callback for store operation. Simple. A little bit of syntax here. This is so-called pointy block. It's another kind of, it's something in between a block and a subroutine. It is anonymous, but it doesn't have a name, but it has arguments. And the single dollar here is actually tells us that we do expect an argument here, but we don't need it. So we just say that, yes, we know there's going to be a parameter, an argument passed, but just ignore it. We don't need it. We can do it like this. Because actually this code is going to be invoked as a method, and we're going to have a proxy instance in this argument. But it's irrelevant. And then what we do, we just try to read from proxy here and here, and then we assign to it, and then we read again, and then we just try to introspect it. And this is very simple proxy object, which just increases counter on each fetch operation and changes it when something is stored. Well, this is not fun yet. This is rather boring, but we'll come to it. So as you can see, we have two reads. They correspond to those two lines. Then we have one store, this one here, and one more read. So the counter is now 11 because we previously put 10 in it. And introspection of proxy gives us apparently proxy. Simple. But anybody noticed how I do it? I do assignment to another scalar, and then I do say on it. Here is the reason why. I told you that proxy can result in unexpected side effects. You see. Here we go. So let's talk about the side effects. Say. I use just say on this proxy. Kaboom! This is our first say. And instead of getting 1, it's the same proxy actually, it's just a counter. So, and instead of getting 1, we get 7. We do second call, and we get 7 more, we got 14. So, what's going on here? Accidentally, when people go this way, they review the way we they reveal the way Rakudo handles calling code objects and the way how Rakudo handles arguments. So what happens here? To make things a little bit more understandable, I have declared this foo subroutine, and it roughly resembles what say does. So it takes a raw argument parameter. I'm still messing up. It invokes method gets on it, and then it sends the standard output. And as you can see, it gives us 7 more fetch calls. Step by step. First, when Raku encounters a call to a multi-dispatch subroutine, 1 second. Anybody, I hope everybody knows what is multi-dispatch subroutine. If somebody doesn't, please tell me. Okay, I think everybody does. So the first thing, Rakudo need to check if the argument matches the subroutine signature. And normally, sorry, slow. So normally this is the way how we declare a multi-dispatch subroutine. First, we declare a prototype. If we don't declare it, Raku does it for us implicitly. It creates a default prototype. So one way or another, it has to match if the argument can be accepted by this signature. So what it does, it takes a value from proxy. First, fetch. Then, yes, it does match. But we have a multi-dispatch. So we need to find a candidate. And for this purpose, compiler fetches a value from proxy again, because now it needs to match this value against signatures of possible candidates. And we have one more fetch. And then it does some internal processing of this value. And because we have row, actually row here as well, each time the compiler deals with the container itself. It deals with the proxy instance. And so each time it needs a value, it pulls it from the proxy, causing another call to the fetch method of the proxy. And so eventually, when it comes to this point, when it finds multi-candidate, the proper candidate, and it knows for sure that, well, it's time to call this candidate, it fetches the value again. But see, the candidate is a row. And so we fetch a value to get the stringification of it one last time. And here, this is why we get all those fetches. Multi-dispatch, signature matching, calling method gist on it, and a lot of stuff which happens behind the curtain, which we don't know about unless we go deep into the Rakudo things. So when you use a proxy, be careful. Be careful because it might be pretty much painful. Look what happens if I add 2 more candidates. You see, the list of fetches doesn't even fit into one screen. 14, 42, how much does it make? 32, 28 calls to the fetch method. So when somebody tells you proxy is slow, now you know why it is slow in certain conditions. But it's really useful in other conditions. It's really, I mean, don't avoid it, use it, but use carefully and wisely. Yeah, that's what I told you about. I promised you some fun. Oops. So let's have some fun. Again, we're talking about symbols, we're talking about objects, we're talking about containers. Let's create, excuse me. Look at this line here. One way, I create a variable which has a callable signal, but I bind it to a proxy. And in this proxy, well, it's pretty much simple. I get a random value, and if it matches the conditions, it fires, and if it doesn't match the condition, then it misfires, so we just have a click. But we cannot store into it, so we just type. And then we call it. We call it as we would do with a normal subroutine. Russian roulette, as they call it. Once again, roulette here, it's not a subroutine, it's not a code object, it's a symbol. It's a symbol which is sigled with callables as a callable one. So what happens technically in this case? Again, Rakudo compiler installs code which looks up, this symbol in this symbol table. Then it takes the object bound to the symbol, which turns out to be a proxy. Compiler tries to get a value out of this object as it would do normally. And in this case, proxy steps in. It intercepts this fetch operation, and it invokes our callback, which decides which of those two subroutines we must call. That's it. I think one thing I wanted to mention, I mentioned a while ago, but forgot about it, is that actually Raku is very consistent. Remember the case with hashes, where they inherit from hashes and behave exactly as hashes? So you talk with them, like you don't care whether it's a stash or a hash. This is an example of Raku consistency. And here we have just another example of Raku consistency. I mean, a thing which is expected to behave as a callable do behave as a callable, no matter what's behind it. There was, yeah, question. There was different, very different options to implement. So, well, I could have launched a run -ref for that matter as well. So why not? And wipe everything out. Probably last thing I have to touch here is, after all, if we walk if the compiler works with symbols in first place, why do we need sigils or sigils? Sorry, pronunciation. So why do we need them? Well, they provide us with meaningful defaults. Remember the example where I was introspecting different symbols and I was declaring them using different sigils, like this one. So apparently we get an array, a hash, a scalar. That's it. What if we don't have sigils? Wow, really? Just compare. Why do I have to type all this? And moreover, actually, when, as I told you about parameters, this sigil stands not for array. It's just the default that the compiler uses to initialize this container. But this sigil stands for a positional, which is more basic thing. And we can actually do something like this. And we get a list instead. Well, of course, we can bind this list to a scalar, no problem. And then we get an itemized list. But what if we don't need an itemized list? So, I mean, there are variants. So sigils provide us with meaningful defaults, which simplifies our life. One thing. Another thing, when we use training code, then we make code more readable. Because really, when I see somewhere in the middle of nowhere, I don't have to, crawl across the code, find where the symbol is declared, find out what type it has. What for? I know it's a positional. It should be a positional. Well, as I showed you before, it's possible to change it and do some kind of trick, but we better not. This is not recommended. So most of the cases, if you see this symbol, you know it's positional. If you see this symbol, you know it's going to be hash or something hash-like, because again, this sigil actually stands for an associative, which is also more basic kind of thing. And because of those defaults, you also don't have to specify parameter types too often. So in this case, the subroutine expects a positional, and if we try, we get an error. Pretty much expected error because this is a string. It's nowhere close to positional. Well, this is one more way to introspect. Here we just take our subroutine symbol and take its signature object. Also note that how much everything is an object in Raku. Signature is an object too. It's a property of subroutine. And parameters of the signature are also objects. And so we can iterate over them and find out all the necessary information. Like in this example, you see, we ask for the first parameter and we ask what type it has. And it tells that it's a positional. Simple. Good. Any questions? Okay, and if no more questions, I have a question then. We are pretty much beyond 4 hours limit, and well, I have considering how much time did it take us to get as far, I probably need another hour or maybe a little bit more to complete everything, all the subjects I prepared for today. But do you want me to continue or is it too late already? Because I know in Europe it's, yeah, 10 past 11, that's quite a time. So what would be your opinion? Shall I proceed or shall we call it a day? Okay. Okay. Just give me a second. Good. The reason why I decided to ask you at this point is because, as you can see, we're gonna switch over to a completely different subject here. Everything I told you before, it was mostly user point of view, let's put it this way. So it's things which you're gonna use in your everyday programming in Raku. Here we will switch more into internals of Rakudo compiler and see how things works internally. And this is really interesting. Actually, when I started with Raku, it was still Perl 6 back then. One of the first things I stumbled upon is that with Mu, I got used to lazy attributes. Okay, let me finish. As you maybe know, Raku doesn't have lazy attributes as such. And I was missing them pretty much, so, well, I decided why not to implement them. And alongside with laziness, also some other functionality which is not present or was not present in Perl 6 back then because some of it has been recently done. And so I started writing my own version of attributes and found myself crawling a lot in Rakudo sources and finding things which were simply amazing for a newbie. And that's how my path into Raku development started. So now I have two things. I have EtherX Muish module, and I have a membership in Rakudo core team. Both came as a result of this simple wish, simple desire. So, as I told you before, I hope that at some point you're gonna be interested in participating in Rakudo development as well, and I hope that your path into this direction will start somewhere around here. Well, I can continue today if you want. I can continue. It's I'm not that much tired, and maybe maybe our European participants would vote for another day. So what would you say? Okay, okay. I have water. I have a little bit of coffee. So let the marathon begin. Well, continue. Remember I told you that the three components of Rakudo compiler, the compiler itself, the compiler as an object which is responsible for syntax and for code generation, meta model, and the core, how they interact with each other, that they're tightly bound together. This is what I'm going to talk about right now. Very simple example. Again, I promised not to talk about syntax, but again, we're talking about syntax. Of course, what we get here, we get 3. Actually, we can do it other way around. We can do it like this. And we get the same outcome. Why? Because technically what happens here, when the compiler encounters an operator, it looks up for a symbol which starts with this prefix, depending on what kind of operator is it, of course, because plus is infix, we also have prefix, we have circumfix, and we have post-circumfix. So in this case, we have an infix operator, and so the rest of the symbol must have this look. And so Raku does not sum for us. What it does, it calls a subroutine infix colon plus. That's it. And this subroutine, it's here, and it is one of the core symbols defined for us. And what it actually means, let me see, no, I don't have it. It means that because it's a symbol, we can change it. What am I missing here? Okay, sorry, I came unprepared for this one. Where is it? Here. Look, I added those exclamation marks, know precisely that it was our subroutine call, not anything else. And look that as a result of this call, of course, this is a bad place to do. It's clear. Here. because it must look as an operator, but you see, the outcome is totally the same. So what exactly happens here is that the compiler installs a lookup of this routine infix plus. And because the core setting is our lexical outer, we can override lexicals, and we do override this routine. And instead of calling the core version of this routine, the code calls our own version. This is how you can redefine operators in Raku. Just brief insight. As a matter of fact, in real life, we usually need to declare it as multi because the original infix plus is multi, and we have to type those parameters because we don't want to catch up with every parameter. But again, it's another subject. That's too much. And I would like to proceed further and talk about less apparent things. What happens here in this example? You all know that eval is a very dangerous operation which caused a lot of headaches to security engineers across the world. Sometimes consequences of using this function was really dramatic and disastrous. So Raku takes care about this, and whenever it sees eval applied to scalar, it issues an error because eval is a very dangerous function. But we do need it. We know exactly we need it. For example, eval is used extensively in test module purpose. So to let the compiler know that we do it intentionally, don't be worried about it, we use this program, monkey see no eval. It's a kind of fun Larry likes, as far as I understand. I think it was his idea to call it this way. So, and as you can see, it was eval successful. We got output of the code we have in this string. What exactly happens here is when the compiler crawls over the lines of our code, it encounters this program and it raises a flag that, well, okay, if you see an eval with a variable, don't worry about it. That's okay. There is another way to do it. It also can call a subroutine with the same name. And if the subroutine returns true, it's also a signal for the compilers that it's okay to have this eval. So what we can do, we can intercept this kind of call and do whatever we need. For example, we might try to determine whether this eval is legitimate or not based on some conditions, or maybe we can turn it on or off dynamically depending on what kind of environment we are running in. It depends. We can do whatever we want. But the point I'm having here is that you see this subroutine is never invoked explicitly, but it's been invoked by the compiler. And when this subroutine is invoked, it also poses some interest, but we get to it somewhat later. have a note that we might possibly consider. Oh yes, that's another fun example. Remember I told you that if you create a symbol on process namespace, you get a dynamic variable. Well, there is another way. Actually, when the compiler encounters a reference to a dynamic variable, it doesn't resolve it directly, but instead it finds a subroutine named dynamic, and apparently it looks at symbols, so it looks for symbol ampersand dynamic, and then when it finds it, it invokes this subroutine with variable in question, variable name in question. Here we go. This is the output we've got from our subroutine. And then you see I redirect the call to the original subroutine. It's also possible because of another pseudo module named core, which has all the symbols defined in core. Sorry, what do you mean levels of danger? Okay. Yes. Okay, this we spoke about. Yes, because compiler needs to deal with the type system. It also relies on meta model to know how the type system works. Sorry, William, because I started another subject, I still don't get what you mean. So when, please ask me again a little bit later when I'll be over with this subject. Yeah, so back on track. So it relies on meta model, how to handle type system. About the core setting to provide static symbols, I also just shown you because this is an example. Dynamic is defined in the core and the infix plus also defined in the core. So this subject is covered. With regard to meta model, we need to get a little bit later to it maybe. Yes, we will. And yes, I also just shown you how some core routines involved directly. Dynamic is one of the core routines which are involved, straight away. So it's time to move on and see what happens when we declare a class. Because this is the point where meta model gets extensively involved. As I showed you before, classes are backed by class how meta model classes, meta model class. What happens internally? How exactly a new class gets declared? So in this example, I will try to roughly reproduce all the steps compiler takes to declare a class. First of all, compiler doesn't know about classes. Really, it doesn't. It knows about the keyword class. And it approximately knows that it's kind of a package thing. I mean, class is a kind of package, not exactly as in Perl, well, that's a different story, but, well, in some way. So compiler has to find out how to create a class. And the first thing it does, it takes a namespace called expert how. Oops, I always expert how, and it takes a symbol named class defined in this namespace. And this symbol is expected to be bound to the meta model class, which would implement the class functionality for us. So let's have a look what we get from there. Okay, pretty much expected. We get meta model class how. Okay, let me skip this one for now. It's not really relevant. Next step the compiler does, it takes the meta model class it found and it explicitly asks it to create a new type and gives this type name foo. This is where we get, once again, this is where we get a type object for our class. Once again, type object. I mean, the concept of type in Rakudo is pretty much extensive. We have classes, we have enumerations, we have packages, modules. They are all type objects. And classes is just one of the type objects, one of many. So new type creates a new class for us. I wouldn't be showing you the code of new type method, but you can find it yourself. Just grab over Rakudo sources and look at class how. But internally what happens is first a new instance of class how is created. And then method new type is called on the instance of class how. And what we get as a result, we get a class type object, and we get a meta model object which is bound to it. So for each individual class, we always get one individual meta model object responsible for it. And this is the one we get with .how method as I shown you earlier. Next thing, we need to add a method to our new class. So for simplicity of introspecting things, I just assign it to a symbol here, because I would like to output some information about it. Then let's say that the class declaration is done like this: class foo does R, which means that we want a class foo which would implement role R for this purpose. This is how we do it in meta model. And this is the code which actually does compiler when it adds a new role to your class. Then we actually add a new method and we specify which method name do we want. You see the point here is this is the name which is going to be used to install the method as a symbol into our class. And this is the name which will be assigned to the method object. Well, if it's not clear to you what happens, you can simply change this string here, or you can change method name and then try invoking different kind of methods on this newly created class and see what happens. And you can also introspect the method and see what it reports to you. It's going to be also some kind of fun, but eventually you'll get used to it. And the final thing our class has to be finalized. And this is what we do with method compose. So in the end, we have a fully fledged class. We can work with it. Here is the method we're going to install. Here we just reported our class. So we have class full, fresh and new, shiny class. Then we can call method full on it. Yeah, first we instantiate the class, and then we create it, and then we call method full. And then we call method bar, which is actually declared by the row we consumed. And it also works. Oops, we just created a new class manually. Everything is possible. So what's the point of this example is I wanted to show you the way compiler interacts with the meta model. And because I tried to reproduce what compiler does, well, it's a way to show you how compiler uses our meta model in first place. And so on, and profit. Yes, we got a class. And you know what? I have a bad feeling that my throat is probably getting really bad. Just, you know, unexpectedly a little bit. So I probably would stick to the proposal to split this talk and to finish it on the last day when I get better. So if you have any questions, I would gladly answer them now. So, but otherwise, I think I'm sorry, but we would better finish for today because tomorrow I have another talk and I better be able to have it. Okay. Hello, everybody. I think you can now hear me, I guess. Now, to share the screen. Yes, and I would like to see the chat window. Yes, I have it. Good. So, okay, let me start with words I wanted to use in the previous episodes of this show, and then you know. So yes, I would like to get back to one of the previous examples I was showing you, not really examples, but a benchmark. Those who was with me on Saturday, okay, I need to concentrate now. You remember that when I was discussing different performance of loops when we use like direct conversion into an array, coercion into a list, and decontainerization. And I was showing you that, tried to show you that decontainerization works the best. Let me not get back to the reasons why and so on. And if somebody noticed, I actually had to switch to another window, to another tab, and to another server to run this performance test. The reason is because most of the examples I do on my MacBook, but when it comes to performance testing, everybody knows that notebooks are pretty much aggressive in throttling when necessary. So if it gets overheated, you get it much slower as an outcome. And talking about benchmarking in general, we have a couple of benchmarking modules in the ecosystem, and I use neither of them. Even though they can provide pretty much extensive interface, I mean programmatic API interface, they could be very much informative, but they all do one big mistake. When you have a couple of tests to compare, they run them sequentially. And what we get on a notebook, the first test warms it up, and the second test and subsequent tests, they're getting pretty much slower CPUs. So the result of your benchmarks on notebooks, it's basically useful. You don't get real numbers. Even if you run them many times in a row, frequency of the CPU, it's floating and changing over time. So I had to use my home server, which is a desktop, apparently, and it also throttles. But sorry, it doesn't throttle, it boosts its speed, but at least it's more reliable. And with boosting, I can fight. I have an approach. And this approach I wanted to share with you. On Thursday, I just thought that we don't have sufficient time, so I skipped this part. What's the idea? It's extremely simple. I just start them. Each test is started synchronously in individual threads. And actually, William, yes, thank you, reminded me. I have to stop one service which actually consumes network, and it might start anytime. One here and one here. Okay, now we are safe. Sorry for this little delay. Okay, so it's really, idea is very simple. As I told you, we start individual threads for each benchmark. And then I use the synchronization technique, which I spoke about yesterday in test async, where I synchronize those threads so they start as simultaneously as only possible. So they report that they're ready, as the main thread then fires a starter gun, which they all await for. And then it's only up to the thread scheduler to decide how synchronously all threads will resume. So whenever you need to do a benchmark, just keep in mind that subsequent benchmarking will pretty much likely provide you with biased results. And if you can, try to do it simultaneously. That's much more reliable. With benchmarking is special. Yes, optimizer also can step in. Though usually when you do benchmarking, one way or another, you repeat it for many times, and there are good chances that optimizer will step in for each test code anyway. So the result you will see, it will usually be the result with optimization already applied. So I wouldn't be that much worried about it. That actually reminds me about another interesting case, but I'm not sure if I can. Which one was it? Block trace, I think. Yes. And this block example, where I was trying to show you the difference in dynamic chain, which is code stack, and lexical chain, static chain. And I was, okay. So I was dumping symbols, and I was relying on symbol names to determine which frame they're coming from. And as you can see, I use dynamic symbols. The reason why is because optimizer could also step in here and use of basically lexicals. Well, no, it didn't work this time, but it's very likely that on occasion you can find out frames responsible for those two blocks to be joined together by inlining inner block into the outer block. And when you use dynamic variables, this guarantees that this kind of optimization will not be applied. So when you're worried about optimization or worried about preventing this kind of optimization, it's also worth remembering about. Okay, now back on track, and let's continue where we stopped last time, where my throat actually betrayed me. And so once again, in a previous episode of this show, we spoke about interaction of compiler, meta object, meta model, and the core. And where we ended with was, it was about compiler using meta model to create new classes when it needs it. And we finished with this example where I tried to reproduce approximately the sequence of actions the compiler takes to create a new class. And I think I was over with it last time, so we can safely move on and talk a little bit about different stages about code lifecycle, because this is a subject which is, well, quite often I use the word confusing, because really it is confusing. Some of the approaches, Rakudo and Raku as a language and Rakudo as an implementation, some of the approaches they use, they're pretty confusing for other more traditional, I would say, languages. So whoever is used to compile languages like Rust, C, C++, whatever, they use to pure compilation. Others, like those who came from Perl, they mostly used to clear interpretation, and we don't really much care about the compile time, which Perl also do. But it's so much hidden and it's so much unapparent that we barely think that about the fact that begin phasers, which are present in Perl, they're compile time things. Usually we don't care about it, but in Raku, it worth keeping in mind and knowing clearly when actions take place, because Raku is pretty much specific about it. And to see start the subject with, I would start with this example. What's in it? Well, it's the module. It's a module C times 0, which we should care about. And the module is also pretty much simple. It has one begin phaser and it has one say. And yeah, just to make sure. If we try this example, well, we see that here is our phaser. It's done. And then we see the say from main line. So far, so good. Next time you run it, and oops, no phaser. Really confusing. And then I go back. I think it's some kind of bug. So, okay, what if I put another thing here? One. Oh, phaser is back, but wait, it's second. What will, and phaser is gone. And this is a kind of what situation which many people come through. I think by now, when I mentioned compile time specifically, you got the idea. Begin phaser works at compile time only. So when you run this example second time, after you change the module, there is no need for Rakudo to compile the module again, because we have what compiler does. It creates a hidden directory .precomp, which actually contains precompiled data for our module. If you try hex dump, I think, yeah, this is it. If you try and hex dump it, you will find this string here, more VM, which tells you that this is more VM bytecode. So if you want to know more about this, I think you can spend some time with playing with it a little bit more. Better move on. Another example, and basically, yeah, I remove this hidden directory. Currently, we get back to the example, and we see that phaser has been run again. We remove the directory because we enforce the compiler to recompile the module. And also, when I was using, say, one here, I think it is more clear now why begin was going first, because first we have to compile and then we actually run the code. Yeah, I shall also tell it. It also might confuse for the first time, but the way modules are loaded, when we request a module, what Rakudo does, it pulls in the bytecode, no matter where it pulls it from, whether from precompiled storage or whether it gets it from the compiler because it just been compiled, whatever. The first thing Rakudo does, it executes the module code it received. So one way or another, whenever CompUnit is loaded, you remember CompUnit. So it's not about module as such, but it's about the CompUnit, and it's CompUnit which gets run by the compiler, actually by the module loader, but so it's a little bit fuzzy things anyway. CompUnit code gets executed, and CompUnit also starts module code and so on and so on. So This is why I used word mainline here, because this is mainline code which is ran whenever our module gets loaded. So we can do a lot of things at runtime if we need to. Next example, we again use a module. And this example also refers back to monkey see no eval subroutine, which I was talking about a while ago when I was showing you how compiler interacts with user code and how it uses symbols provided by user code for its purpose. Okay, so let's try it first and see what happens. Monkey sees nothing. This is the code of our monkey see no eval. And then it's our foo being executed by the script which consumes the module. And this is where I get this say OK, and the OK I get here. So we do the same thing, we try it second time, and we get no monkey sees nothing. Again, I think the reason is already clear. As I told you, monkey see no eval is invoked by the compiler. And compiler does it while it works. And what time is it when it works? It's actually the compilation time. So no need to compile, no need to call monkey see no eval sub, no output. And this actually means that this subroutine is being invoked at compile time. And this is really extremely interesting how things are done internally, because we are used, again, the traditional compiling languages. They got us used to the fact that until our code is compiled into something final, into some kind of binary code, we cannot use them. As far as I understand, Rust, correct me if I'm wrong, but I think Rust has changed something about this. Not sure, but again, so let's see step by step what happens in this example. So the compiler starts compiling the comp unit to which our module belongs. Well, this line is clear. This line is clear, so it crawls line by line, and then it gets to the subroutine, and it compiles it. But at this stage, I think all of you has already, well, it's more, okay, have already seen Jonathan's presentation about Raku AST. And Jonathan mentioned that currently we use CompAST, how does it pronounce it? Cast? Yeah, cast. So we currently use cast for compilation, and cast is actually what gets translated into the actual MoreVM bytecode. So when compiler comes to this point, what we have an instance of sub object, an instance of subclass, which is initialized. I mean, it's a fully fledged object, actually. Really, it exists. It has some of its attributes initialized, and it you can ask for its name and so on, but there is no bytecode for this subroutine yet. The bytecode only exists in the form of cast tree. So this the subroutine is basically half-baked at this stage, and that's fine. That's really fine. When compilation ends, in a normal situation, the compiler will, at the end of compiling the CompUnit, the compiler initiates translation of cast tree into bytecode, and everything, including the sub object, gets serialized and stored in that precompilation file I have shown you before. But not here, because compiler continues to crawl line by line. It encounters another subroutine, it starts compiling it, and it finds eval with a variable. And as I told you previously, compiler considers it as dangerous, and it wants to find out whether it's intentional or is it a mistake on our side. And in doing so, it apparently first checks if a pragma monkey see no eval was used. No, it wasn't. And it tries to find the corresponding subroutine with the same name. And it finds. But the first thing compiler sees is that subroutine is not ready yet. It's stopped, but not compiled. So what happens at this point? Compiler completes the compilation by translating cast tree into bytecode. So it does it preliminary. And at this point, we apparently get our monkey see no eval subroutine compiled and ready to be used. And we have bytecode for it. And that bytecode compiler is using to invoke the subroutine and get the return value out of it. And all this happens at compile time. And even more confusing, it is possible that a subroutine invoked at compile time, or just any code, not necessarily subroutine, any code. For example, if we use a begin phaser, it could be used with a block, and the block gets compiled, so it's called. And within that block, we again can declare a subroutine which will be invoked at compile time of this. I mean, okay, let's not get over there. It's really complicated, but things could happen this way. There could be nested levels of compilation. How do we know that when our subroutine is invoked? 1 second. I think monkey see no eval is special, but we can check this out actually. It's in, I just don't remember. No, it's probably in the world. Monkey see well. And it's probably options. Pragma. And actually here we go, this is, yes, this is in actions. Here you see the code which actually calls our subroutine. So what happens here? Compiler, and it gets us back to the previous subject, big subject I was talking about, symbols. So as you can see here, compiler finds a symbol, monkey see no eval, and then it involves it. And as far as I remember, monkey pragma, yes, as you can see, it's only monkey see no eval which is special in this respect. So the compiler only looks for this subroutine when necessary, no other monkey pragmas. It could be implemented if considered useful. Was it useful or not? I don't know. If you want, you can open a problem-solving case, and you know the procedure. And it's very likely that Jonathan will come and say, no, it's useless. And he will put it in the way that you will understand, yes, it's really useless. Well, though maybe not. Who knows? Time, yes, I think it's over with time. So how do we know if our code has been invoked compile runtime or compile time? Normally, there is no clear indication, nothing that is documented or guaranteed to work. So you would just know that your code at this point will be invoked compile time. So you just know it. But one thing which will be gone as soon as Raku AST will land into the master, but for now it works. Or like so, as you can see, on the first invocation, which happens at compile time, we get a name, and on the second one, we get a failure because the symbol simply doesn't exist. I can even do like this and get the dynamic variable not found. $*w, it's a shortcut for vault. It's an object which is responsible for holding all the information, grammar, and actions. So basically our compiler considers necessary for the evoke, and also this object has a lot of helpers. It provides a lot of templates for cast tree, for example, so that you have a limited number of parameters. You supply them to some of the methods of this object, and as an output, it will provide you with a ready cast tree, which you then simply plant into the tree you built at the moment. But this object is almost in deprecated state, I would say, at the moment. Because as I told you, when Raku AST comes, it doesn't have this concept. It's implemented totally different way. So, completes compiler. 1 second, it's just when I see some notes for myself. Yeah, I probably have missed nothing here. And yeah, I have completed at this. As I mentioned it in the beginning, all three components are heavily tied together and they rely on each other. And at this point, I have shown you how the compiler uses our meta model and how it uses user code and apparently core code, because also remember that our CompUnits, they're simply lexical internals of the core setting. So whatever symbol compiler may need, it may find it either in your code or it may find it in the core. So there is no big distinction between core and user code in this respect. But okay, the core code also uses compiler. And this part is a little bit tricky to show, but the best example of how it happens would be probably to get one of the traits implementation. And Okay, and here we go. Okay, but by this point, I hope that you know what traits are and how they're used. And this is an example of how a trait is being implemented. It's deprecated trait, so that when we know that some method, so we cannot declare, but method foo, something like this, is deprecated, and if somebody tries to involve this method, they will get a warning that, okay, you use a deprecated method, please do something about it. Briefly like this. The way it works, the trait takes a routine object, which could be anything. Routine is a role, and our method sub method, they all inherit, they all consume it. Or is it a class? Okay, I'm sorry, I'm a bit confused, but it doesn't matter. Routine is the base thing here. So it takes this routine and it installs an interfacer. So what we do it manually, it would look about this way. Just again, roughly, something like this. But the point is, phasers are installed at compile time. And this will not work otherwise, but by referencing to the compiler and by telling the compiler that you have to install a phaser into the code of this routine. And could be mistaken. Let's see. Yeah. Otherwise, as far as I remember, there are no more use of compiler by the core. So, and this is actually a good practice because one way or another, but it's our standard library, and it's better be clean and neat. But there is a legal way where adding a phaser is a little bit of a trick because I don't remember it to be standardized by ROST. But a legal way to use compiler is again to use begin blocks. And begin blocks are certainly utilized extensively across the core. Like, for example, recently I have fixed a bug about native integers, and not only integers, where they were declared as inheriting from int type, which wasn't complete by the time when it was used. It's possible to do things to happen this way. So you have a class, you already know that this class exists, but it exists as a type object, but it's not complete yet. It gets us back to the compose meta model method which we used previously. So until a file is until a class is composed, it's not ready, and natives were inheriting from incomplete classes, and therefore they were lacking information about type matching on the type matching because roles consumed by integer were not known yet at that point. And what core code does when its compilation is almost complete, at the end, in a begin block, which is executed at compile time, but just it's the end of compilation time, they simply recompose those native types So they pull in all the necessary information from their parents and type matching against consumed roles like numeric, they start working. So begin block in this case is used absolutely legitimately. Sorry, some issues with pronunciation. I'm still having them. Contrary to the compiler, core is very extensively using metamodel. This is where we have a lot of things happening. So if you get back to traits, you can make this kind of search, and you see we have 1, 2, and 3. There are going to be many, just really many. Let me try it like this. "52 lines of code in traits referencing to the metamodel, and it's only in traits file alone. And you can only imagine how many references to metamodel methods you can find in other files of the core. So I lost track a little bit, but really, the thing which probably worth mentioning, though I didn't plan it, since I use traits as an example, traits is really a good example of a subroutine which is used at compile time. Traits are applied as early as possible. So, for example, when you apply a trait to a class, like here, if I remember, it's one. Yes, it's how inheritance declaration is implemented in Raku, actually. So when you do it, class foo is bar. At this point, you get this trait involved. And because it all happens at compile time, this trait safely add parents to incomplete yet class. And when this trait finishes its work, even though our class is still incomplete, but it already has the information about its parents. And when the compiler finalizes class compilation, it calls composition on that class, and we get all the parents used and everywhere when they had to be used, like in type matching caches, whenever. So whenever you decide to create your own trait, remember that your code is going to be executed solely at the compile time, and take all the necessary precautions to be safe about it. And again, metamodel and compiler. Metamodel really doesn't use compiler code a lot, and also it's a good. Usually, it's a good thing because it's better to be agnostic of what exact compiler is using it. Like I said before, it's possible that at some point Rakudo will be not the only Raku compiler, but the other compiler might base itself on the metamodel we already have. It's possible. So the less we rely on compiler internals, the better for the language. And the only thing which metamodel cannot live without is it has to know what is the current language version is requested by the user code. And this is the information only compiler can provide it with, because it's the compiler which deals with use with its pragma and which sets the actual language version. And metamodel does use this information on several occasions. For example, if you ever use subsets, you might find out that they look differently, slightly differently, or not slightly differently, in 6C version of the language and in 6E version of the language. And this is because this code is actually depends on metamodel, and metamodel does it differently, does it more correct in 6E version. Yet sometimes metamodel expects also our Raku code and core code to provide certain symbols for it. There are two ways how it happens. One I have shown you with the actions class and monkey see no eval example. It's when the vault object is used and find symbol method is used to locate a necessary symbol. This could be seen, for example, in model NQP. I use this code because it is mine. Oh, sorry, it was initial idea, but then I had to change it. So it's another mechanism I use. Okay, let's not get that deep, and just know that metamodel also uses symbols provided by core, and this particular code here, it's about exception throwing. There is a problem about metamodel code where it was a period of time when it was more important to get the code working than to get it working the right way. And many cases where metamodel must react to an error of some kind, it uses, like in this case, though here it's done intentionally, it uses simple die, which throws the most simple exception type, ad hoc exception. And ad hoc carries no other information about what exactly went wrong, but the message it is supplied with, and nothing else. And well, of course, it's really hard for user code to find out and to decide how to behave if it encounters an exception thrown by metamodel, whether it should die further or it can do something about it to fix the problem, because really the only way we can know what exact kind of problem happened is by parsing the text message, which can change at any moment of time. So to fix this situation, a mechanism of exception registering was developed at some point, and it was too complicated. I simplified it a little bit in this code. And what meta model does now, when it knows what kind of exception it wants to throw, and it knows that this kind of exception has to be provided for it by Raku code, it tries to look up this exception in a registered namespace. And what Raku code does, when it has this namespace available, in particular, it's x : Raku registers this namespace with the meta model, and from this moment on, meta model can throw good exceptions, correct exceptions. And the way it does so, it gets exception name and it looks it up in Raku symbol table. So as I told you previously, meta model uses symbols provided by Raku. Okay. We are done with interaction of compiler objects. The thing is, I understand that it might sound obscure at the moment, but I hope that at the point, at some moment when you go into the source code of Rakudo, something of what I said today will pop up in your head, and it will be much less confusing for you to understand what exactly happens. So just hope it works this way. Sorry, Konstantin is asking, is saying that it's built in, what exactly is built into it? So if you could please elaborate a little bit. And in the meanwhile, we actually came to the final subject I wanted to cover with this class. And however, it may sound simple, people do a lot of mistakes when it comes to object construction in Raku. In particular, again, in Rakudo implementation of Rakudo. So what could be simpler than declaring a class and then creating an instance of this class? But then questions come like, for example, okay, why does it take only need parameters? What if I want positionals? Or what if I need to validate some parameters and take some actions at the construction time? When exactly do I do it? And well, a lot of other questions, and I hope to cover, if not all of them, but most of them. I hope I can manage it. So again, however simple it looks, but as a matter of fact, when you create an instance of a class, it's a process which takes quite a long path, and a lot of stages are involved into building a new object. And I'm not even talking about creating a class in the first place, because we spoke about it earlier, and well, it's not really a part of object creation in a way, but no. And of course, it starts with method new. Not necessarily new, it could be any method. After all, we talk about Raku, and Raku, everything is possible. There is nothing impossible. But normally, yes, it starts with method new, which is defined on class new. This is our first stage. Let's have a look into class new. And here we go. Method new is pretty simple. And it's not at all magical. Absolutely not. It has two candidates. The first one takes named parameters only, and the second one is accepting positional parameters, but the only reason it takes them is to throw an exception saying that we don't support positional parameters. So this is the default behavior, and you get it automatically because any class declared automatically gets class any as its parent, as I told you, and any has new as its parent. So simply just by inheritance, get method new. What happens next? Next, we new uses bless, and in turn it uses NQP create bless method. Though it might be okay, don't try to analyze this code. I will explain it verbally. So now let's go to class to method bless and see that what bless does. This NQP create, it creates the object itself. So at this point, we already get an instance because NQP create takes a type object and it allocates all the necessary structures in the virtual machine to provide this object functionality. And all this process is what we call instantiation, basically, or just the first step of the complete instantiation. And then it involves build all method on this object. The only thing worth remembering is that I don't know why this method bless is presented in new, because new by default gets around bless unless you define your own method bless. So as you can see, this line is normally what you get used when you create a new object, unless you create your own class. Like this. Well, in this case, your method will be involved instead of the default one. Well, probably it makes sense because in your method bless, you can then pass control back to the default bless if you don't want to create, instantiate the class manually, whatever. One way or another, I must admit that I don't really understand why we need method bless in first place. Probably it's a reference towards Perl, where bless is the default way of creating an object. Maybe. I don't know, probably something historical. I never thought about it, so just take it as granted. But let's move to what's really important. Let's move to method build all. It's also a method provided by new, but this method refers further down into meta model, and it takes a build plan from meta model. Here is what it means. Okay. This is the line where it finds build. Oh, sorry, it's that. Yeah, build all plan. And then it invokes this meta model method. When we talk about a type object, let's simplify the situation a bit, and let's talk about class in particular. Who in Raku model actually knows everything about our class? It's not the class itself. It's the meta model instance, in particular class how instance, which knows all the details about our class. And it means it knows about its parents, it knows about the roles it consumes, it knows about attributes, it knows about methods, submethods, all kinds of things. And therefore, if we want to build a correct instance of the class, we have to ask meta model, how do we do it? And this is the way to do it. Just hopefully I'm not confusing myself. Build plan. Okay. Yes, it's build plan. Yes. Create build plan. Yes. I would skip all the chains of the call chains, which will end up in calling this meta model method. But here, a build plan is created. A build plan is a set of instructions for our high-level code. And by following those instructions, we do one or another kind of actions, like, for example, we create an attribute object and add it to the class, or we create a method and add it to the, take a method code and add it to the class, and so on, so on, so on. And then we can call certain submethods and we'll get back to it, whatever. So build plan is the plan our high-level Raku code is using to build our object. And it is created by meta model, because meta model is the only place where they really know how to do things. And basically, if you check build all any further, it's really, really scaring kind of thing. So NQP while iterates over our build plan, and then you will see a lot of NQP ops. So it's terrifying. I'm not going, of course, I'm not going deep into all this. Don't leave any traces behind. It's not that you would need to use this plan on your own, unless at some point you decide to create something which goes that deep into the process of building an object. But what we need to know is that parts of this plan are invocations of two submethods, build and tweak. And those two are basically finalizing the whole object creation sequence. By the way, I actually had an example, but yeah, this is what I intended to use to show you how method bless is used. So as you can see, our method bless is involved in creating objects. Nothing really serious about it. What is serious is how do we deal with build and tweak, and what's their role, and why are they so important for us, and why are they submitted in first place? Well, anybody needs to know what makes submitted different from the usual method? Do I need to focus on this? Okay, probably not. But one way or another, I just would like to remind you that a submethod is not inherited from a parent class. It's a sole property of the type object it is defined in. And so if we try to invoke submethod on a child class, we'll get an error. And when it's applied to build and tweak, yeah, we'll get back to it. When it applied to build and tweak, it means the following. The way the meta model builds build plan is that at the final stage, it iterates over this MRO order. I think you remember this method. It's method resolution order. I used it previously to see the inheritance chain of a class. And here, as you can see, MRO tells us that methods are to be resolved in this order. So if we look for some method foo, for example, we look for it on bear, on foo, on any, on null. If you look for new, we look for it on bear, on foo, on any, on null. Good. But what does it mean for build and tweak? It means it has reverse meaning. When build plan creates entries to for those two methods to be invoked, it looks for them in reverse order, so that first it tries to find build on null, then on any, then on foo, and then on bar. Somehow when I was writing this, I see. Yes, this is intended for different purposes. So first we do it like this. And here you see tweak submethod of foo was invoked first, and tweak submethod of bar was invoked second. And why is it important for it to be submitted? Because when build plan is built, meta model uses normal method lookup approach to find those methods, submethods. So basically, it doesn't care whether it be method or a submethod. And therefore, when it tries to look up for, say, for method tweak on bar, it will find it. But the problem is that this tweak method will belong to foo if it's a method and not submethod. So in this example, as you can see, I stripped down the sub part of the method. And if I invoke it, oops, I get the same tweak invoked twice. Of course, it would be pretty normal to ask a question. So why doesn't it look for those methods on those classes explicitly? Why does it use normal lookup approach? Well, sorry. Because in this case, this would put these two methods in a special category. It's like all animals are equal, but some are more equal, and this is no good. Really, it's such kind of situation is always better to be avoided. So submethod in this case is the best solution, because you simply tell explicitly that you want this method to belong solely to this class or to this, well, okay, let's leave it, to this class. And the idea behind it is that in this case, we can guarantee that this submethod knows how to build this particular class and nothing else. So it bears sole responsibility for this particular class and nothing else. And this is clean approach, the cleanest approach you can think about. So always remember, don't make this kind of mistake. Always use submethod for build and tweak. The next thing to remember about is that there was a change in behavior between 6C and 6E. Previously, the approach wasn't that clear. So you see, I put explicit stress on the fact that a submethod is sole property of the type object it is defined in. This is not true for 6C and 6D. Why? Because when you declare a submethod in row, it gets copied over into the class consuming this row. So in this code, we see simple output of row, and we see it exactly because this submethod was involved, but not when we expected it to be involved. If I add a submethod tweak to class C, oops, I get no row. And to get it invoked, I have to be explicit. I can't even use next same, called same, or whatever dispatchers we have. No, I have to explicitly refer to the class name. And only then, yes, I get row and class. I always consider it to be not the right approach, because it's a direct way for different kinds of problems. So in 6E, for 6E, I have changed a lot of things about how roles are consumed and used and so on. And one of the things I changed, I completed the principle of sole proprietorship. And from now on, submethods are really only belong to the type object where they declared. And build plan is built with consideration of this fact in mind, and roles are respected. And for now, for any role in 6C, you can have your own submethod tweak, which will take responsibility for this particular role. This becomes especially important when you have a number of roles consumed. And so instead of remembering to give control to each individual role, you just declare the submethod. So we use declarative programming in place, and it saves us a lot of headaches. Okay, then okay, I covered all this. And You know what? Yeah, before we get to this part, I would like to see if you have any questions. Okay, Daniel, I think I have answered your question already. Because build is part of the build plan, it gets called after build all. So build all gets everything prepared, and then it fires up all other things. So let's talk about a couple of specifics we have here. Also, pretty much natural question would be, why do we have build and tweak in first place? Why not just build? As always, it's better be shown with examples. Let's start with a simple one. We have an attribute, and we have a default value for this attribute. And we want to do something about the parameters we accept when the class is getting instantiated. Whatever, it doesn't relevant for now. So we won't just output them like here, or maybe process them, whatever. And then we have two approaches, because the attribute has a default. So when we create an object and output this attribute, we expect the default value. But if we initialize the object with different value for the attribute, we naturally expect some different value of it. But no, you see, in the first example, yes, we do get default and no attributes. In the second one, build reports the attributes which we passed to new, but the attribute value is not changed. This is the kind of thing which is very easy to miss in the documentation. I do remember it is somewhere there, but I'm not sure where exactly. The point is that unless you supply your own build method, a default one will be created for you by the meta model. Will be created and installed. So if you have attributes with default values or with some other conditions, whatever actions need to be taken to initialize an object properly, except for those you would need to do on your own, all those actions take place in the default build installed for you. This is done again to keep Raku as logical and predictable as possible, so that when you have the most simplistic declaration of the class C, you get what you need. You get default when no attributes was used, and you get the value you supplied in the attribute. Okay, there is a syntax trick in Raku which allows for quick initialization of an attribute. So if you write your parameter like this, it will be bound directly to your attribute, because otherwise you would have to do something like this, which is apparently too verbose, so nobody likes it. Okay, you say, problem solved. We can do everything like this. Well, let's see what happens. Look, the problem is when we pass an attribute value, we really get this attribute value. But not when we use no arguments whatsoever with our new. In this case, we get an initialized value here. And this value gets stored instead of the default value. So again, it looks like a simple way, but simple solutions are sometimes really bad solutions. And if you want to modify the attribute in some way, for some reason, we also get into a problem because it works correctly for the first case, but in the second case, we get something really confusing. And frankly saying, I think it's some kind of a bug because it should throw in here. Because we try to multiply undefined value to an integer, but whatever. For now, it's not relevant. So this approach doesn't provide a solution for us. So from now on, just the way to do things for you, if you don't need anything really special, where build is exactly what you need, tweak is what you need, in fact. Because look, without any big changes, we just replace build with tweak, and we modify our attribute, and we know that it's going to be initialized, no matter what, whether we pass an argument or we don't. It works. So here we got E multiplied by 2, and here we got PI multiplied by 2. So as simple as that. And if you need to know what arguments were passed, you still can use either this way. So you see we get a hash of sloppy arguments. Or of course, you can use it this way. Whatever. It is simple. This is simple, pretty much predictive solution, which covers 99% of all cases, even 99.99, whatever. Okay, but what if, really, what if I need my own logic for constructing an object? What if I want positionals, for example? How do I do it? Apparently, tweak is not a solution here. It wouldn't help you because even if you do it like this, just better. So, kinder, we expect tweak to accept a positional. It will not work. Nice. That one. Would be the correct test for it. So things on the fly. Yeah. So we get this common error because it's new, which doesn't accept the positionals. And changing tweak apparently is useless here. It wouldn't help us. Okay, no problem. Change new. There is no problem in this. Absolutely. And okay, just yesterday, Jonathan talking about his new dispatch told you that call width is really slow. Yes, it is. But there are other way around to do it, whatever. I mean, this approach for now is good enough for our example. So what I do here, I'm just totally override the default new, because the way multi works in Raku, if you don't define a proto method in your class and one of your parents has a proto method for this multi method, then your candidates will be appended to the list of parent candidates. So if I comment out proto, then I will get a proto from new here. Okay, if it's not clear now, then just skip it and just a comment. Anyway, one way or another, I now have a point with positional arguments, and I can also use named arguments because of the second candidate, which takes all other options where positionals are not involved. So either I get this one broken, or in any other case, I will get this one broken. And it's basically the same. So no matter whether I used positionals with new or names with new, I get the same outcome. You can, well, actually, yes, you can use bliss. Why not? Why not? Let's see. We closed it. No, it's still here. Let me see if we miss anything in this case. Well, actually, no. No, yes, you can use bliss. Probably this is one of the reasons why we have bliss in the first place. So it simplifies. Except that if you do it like this, then you will not get an error. Okay. Apparently, this is an error. Okay, yes. Though error message is not really clear in this case, and we can make it back, but still, I mean, you get an error instantly without. And if we use bless, let's see what we get. Well, okay, in a way it's acceptable. So one way or another, but yes, we can use bless. Why not? Good point, really good point. But anyway, just consider it as my recommendation. When you need any kind of specific behavior for your class, then thoroughly think about using tweak first, whether it can fit into tweak logic, or sometimes it might be necessary to not only to change the signature of the new method, but you may also need some pre-processing for the arguments you are receiving. For example, where did I use it? Oh, yes, when I was developing Vigna, I used an idea from another user interface framework which was developed for Perl called Prima. And Prima used a very interesting concept where when you create an object, you pull in profiles for this object from different sources. By profile, I mean a set of named parameters, roughly saying. So in Prima, it was possible to pull some arguments for the constructor from config file. Some you get from default values, and some you get from the user when it actually creates an object. And then all three are merged together and validated before they passed over to create an object. So you would get unbroken profile for your object, and and it's really convenient when you create a window, for example. All you need to specify is just window size. And then if a user wants different border for this window, you can simply specify this parameter in config file, and your program would pay no attention to this. It doesn't matter. So, and the best place where it fits is exactly the new method. So before creating an object in Vigna, I implemented basically the same logic. So new takes its arguments, then it traverses all the parent classes and roles and so on, and collects default values, and then it pulls in the config file, and then it's all gets merged and passed further. So this is the place where new works best, because when it comes to tweak, in some cases it might be too late already, for many reasons. Primarily because when you merge three different sources of information, it's really important to know the priorities. It's really to know where some value came in from before deciding that other value, depending on it, whether it has to be changed or no. I mean, a lot of logic involved. And when it comes to tweak, all those information is already lost. So you don't have it in tweak. So sometimes new is really good place to play with arguments before creating your object. But other times, tweak is really the appropriate location. And to call it a day, just the last little trick. There is nothing really specific here, but it's really fun to know that it's possible. For type object in Raku, we have so-called invocation protocol. It is called protocol because also there are a couple of stages takes place to decide what to do when type object, oops, excuse me, when a type object gets invoked like this. So you see a usual subroutine invocation here. And the last stage is the protocol checks if there is call me method. And this is just another way to overcome all those inconveniences, sometimes inconveniences, of the new you don't like. So you take any kind of arguments you want, any kind, you have any kind of parameters you want in your signature, and simply call the constructor the way it has to be called with. So you don't need to overwrite new. You do it all here in call me, and then you have this nice tidy invocation of your class. And oops. With that, your object. And well, okay, a lot of comments I didn't need anymore. And that's all. I'm basically over all the subjects I wanted to discuss with you in this class. So yeah, thank you for attending and thank you for your appreciation. I think the question about video is a question to Andrew. Yes, Daniel.
One question from the first part of this talk that you skipped in the interest of time. I was wondering if you could answer quickly, is the difference between lookup and find method. That was on one of your slides, but you said that you wanted to skip it. If you don't remember, that's fine too. But I was curious about it because I wondered that myself and didn't know, and then was disappointed when you said, "Well, let's skip that part."
No, find methods is rather low-level thing which will return you first available candidate for a method. Lookup is a simplified version, which is mostly used for introspection. But you know, to recall what's the exact difference, I think I wouldn't tell it without looking into the code. And you can see the code now. So it takes method table, finds if it's in the method table, sub method. Yes. Lookup doesn't go to parent classes. It doesn't do lookup on the parent classes. So lookups gives you what exactly on the current class, and only that. Where find method will by default, I think it's by default. But again, let me check it. Oh, it's not even here. Yeah, it's in C3 and no. Based method dispatch. That's method. No fallback. Yeah. Oh, and again, lookup will not try to use fallback method, and find method will try unless you tell it not to do. And then, yes, there are a number of named arguments it accepts. But yeah, as far as I remember, it does. Once again. So, yes, it does. It does trace a similar.
Okay. All right.
So
well,
it's
thank you. That answers that question. And thanks for this talk.
Yep. Welcome, and it was really a pleasure. By the way, I have just demonstrated the way I find documentation in Raku. So it's about 50-50. Half of the time I go to the documentation website, and half of the time, this is my documentation. I go to the sources, and often I find much better answers here. So. Any more questions or? Okay, can a role access the list of attributes in the class? It has been composed into it. Compose time. I think yes. I think yes, but the point is that there is no way for Raku code of a role to intercept this point in time when it gets composed into. Okay. Parametric. Yes, it's parametric. Specialize. Body block. Yes. Well, in theory, it is possible. You see, a role body block is gets involved when the role is getting specialized. And basically, specialization usually take place when it gets applied to the class. So probably you can do something from your body block, but then you would have to introspect grammar's dynamic variables to find out the class. Because at this point, class information is probably not available. Well, why not we try it? But yes, yes. You see, class is not composed at this point. So you cannot, you cannot, but the only thing I'm not sure about, and probably it's not that easy, attributes at this point are not installed on the class because roles are getting applied early because they also bear attribute information. And so before attributes are installed, they have to be collected from roles as well. So there are some attributes already installed, some not yet. So this is pretty much unreliable. And to find out all the attributes, you would probably need to traverse both class and all the roles it consumes. But generally, it is possible. It is tricky. It would require you to, a little bit of knowledge about early stages of class and role relationships. But I think in general, yes, it is possible.
Another question occurred to me, Vadim. With that last trick you showed with the call me initialization, how does that interact with the coerce? Because that seems like the same syntax when you had your point. If you had a point that only took one value, that would be the same syntax as coercing from a value, wouldn't it? With the two open bracket, I mean the curly bracket, that parentheses.
Yeah, I got your point. Well, one thing is when you get more than one argument, it's clearly not a coercion.
Right.
So it's a single role in action, single argument role in action anyway. But when it's just one argument, you know, I have changed this code without really deeply understanding all the details happening. As far as I remember, coercion is tried first, and if it doesn't work, then invocation is tried. If I'm not mistaken, we can try it. Let's reduce to 1. And whatever. Let it be mine. Oh no, call me Vince. Call me Vince. Well, it's a conflict. Maybe it means because, but no, I don't think so. Yeah. And Henderson, yes. So just by experimenting. Really, I don't remember. I wasn't getting, I just found out that it's broken and it's passing spec text, and I moved on from this piece of code because it's a little bit convoluted. So especially I was remembering about the Raku AST coming, and this part is somewhere deep in the actions as far as I remember. So actions are going to be gone anyway. So there was no reason to analyze it pretty much.
That makes sense. Thanks.
Attributes. Dan said that asking for attributes on role gives you class attribute. Yes, there was a problem about role application. It was another egg and chicken issue. You see, Raku does not impose limitations on what roles can be consumed in which order, and so for any role you can consume any other role, and if you mix it all together you get diamond dependencies, like R1 consumes R0, R2 consumes an R0, and both are consumed by class C, and R0 declares an attribute, so you have two passes for this attribute to end up into the class. And what if the class has the same attribute name? So to resolve all those diamond dependencies, it was necessary to change the logic a bit. So class attributes are getting installed first, and then role attributes are getting pulled in some specific ways to resolve all those diamonds and resolve all the conflicts and so on. And so eventually, yes, when your role is applied, most of the class attributes are already installed. But if you expect attributes from other roles to be installed on the class, this is not guaranteed. They are probably, they may be already there because of the application process, or maybe they are not. So don't rely on this information. If you ask for class attributes at the time of role specialization, you may not get the full list. That's the point. Probably invocation protocol wins always. Probably, as I told you, I don't remember details. And usually I don't mix things up. So one way or another, I usually try to not to use confusing concepts in one place. If I know that one may conflict with another, I'm trying to find a way around and avoid this conflict whatsoever. So. Okay, any more questions? I mean, as far as I understand, we're not really limited in time. So if you're just shy about asking, well, don't be Well, then I think we are done.